Okay, so I think you can hear us. Do you also see the screen?
Yes. Yes, we see.
Do you see the right screen?
We see the slides.
Nice, exactly. Do you also see, let's make something cool. Do you also see this?
Yes.
Nice. Okay. PowerPoint master. So I think we can wait other 5 minutes because I know that people at 9 a.m. will start at 9 and 5 minutes, even if this is Switzerland. So in the meantime, we can also try to start something useful. Okay. This will come in handy afterwards. So if you want, also from online, you can start downloading already the ARA repo and check out the MP Arathon branch. Just see that everything works. I don't think we have anyone internal from... yeah, we have Ricardo. Yeah, we only have Ricardo, I think. Internal, but Ricardo, you will be able, you should be able to follow the IIS internal README.
Yes, exactly.
Nice. So let's wait 5 minutes. Just let me know if there are problems in cloning the repo, setting up everything, or in the README. So you should clone the repo, and in the README, you should find a chapter that is called the Arathon Special, which is towards the end of the README. Just let me know if you don't find it or whatever, so we can start debugging it now. Ciao, Chris. So yeah, I will start already giving you some informations about this README so that we can wait for the other 2 or 3 minutes. Only because way more people have said yes on the poll. So okay, this is the MP Arathon branch. Yeah, you should find towards the end this paragraph here, Arathon Special. So something important that that will be very useful for you during the Arathon is this document. It's just the RISC-V specifications. So now the RISC-V vector specifications have been moved in the main document of the RISC-V ISA. So you can find them at risc-v.org in ratified specifications. You know, they have merged everything here on this. Hello, on this document. The weird part of this document is that the hyperlinks are not really working. So you will have a lot, like plenty of fun in trying to understand where is the information and reaching it. So first important thing, specifications. Then, as I was saying, I don't know if you received the email and the notification. So for internal IAS people, it will be a bit easier because I already installed the toolchain and we also have access to QuestaSim. For the external people, it will be a bit maybe more painful. I hope you manage to install the toolchains, especially LLVM, Spike, which is really not strictly necessary, but very later if you don't have access to QuestaSim. Okay, more people are joining here. So let's wait until 10 past 9 before starting. So just a brief introduction for the internal people, just to set up everything, if you want to start already, since you didn't start yet. You just need to install the dependencies. You just need to follow this part of the README dependencies on the MP Arathon branch of Ara for the new ones that join now. And you just need to copy my toolchain that I've already installed. This should be relatively easy if you work on Scratch. Then it will be just about downloading the hardware dependencies with Blender through the makefile. Super easy. And then during the hackathon today, I thought not to have like a lecture style session. So this will not be as structured as you can think of a normal lecture. I will try to mix theory and practice a bit so that you will stay awake. And the main things we will do will be writing some C code, compiling some C code and inspecting the assembly generated by the compiler, and then simulating. So if you are using Verilator, you can simulate with Verilator, and the best way to look at what's happening there is using printfs. While if you're using QuestaSim, it will be way easier to use also the waveforms if you want to inspect what's happening inside. Okay. One minute and we can start. Okay, we can start. Do you see the screen again?
Yes.
Nice. Okay. So welcome everyone. As I was saying before, today we will have a bit of fun together, a bit of vector fun. This is called the Arathon because we will talk about vectors. And yeah, it will not be a standard lecture. So we will try to mix theory and practice together. And we will try also to write some code. So again, this is not a lecture, so please stop me if anything is not clear. We can discuss it. If you prefer, you can keep the questions for the end of the slide section. Every section will be marked with a green screen. So if you want, you can keep the questions for the next green screen and ask me. Otherwise, if there's something that's not clear and this is like precluding you from understanding what happens next, please stop me immediately. No problems at all. Just one note, please unmute yourself and ask me loudly because I'm not reading the chat. Okay, so we can start from some fun information. So, you know, today we will talk about vector processors and vector processors. I don't know how familiar you are with this topic, but were pretty famous at a certain point in time in like the 70s, 80s. Well, there was a lot of hype for vector processors because like the Cray X1 very big supercomputers was a vector processor, and it was the fastest one in the world, right? Then, you know, the usual plot that we show, at a certain point, the silicon became inexpensive and designers started focusing a lot on instruction level parallelism. So let's try to run all the instructions in parallel inside our core. Who cares about the energy efficiency? Because the silicon was really inexpensive and the energy efficiency was yet not the problem. But at a certain point, we started hitting a power wall, end of Dennard scaling, you know, and starting exploiting again some cheap form of parallelism and some more efficient way of processing our applications became paramount, right? And like in the last 10 years, vector processors started being designed again. And you can see like the Fugaku supercomputer, it was like the fastest supercomputer in the world. It's based on a vector ISA. And yeah, in 2021, it was the fastest one. This was an old slide that I used. Today is only the 7th, but you know, is still trying its best. So we have really seen in the last 10 years, not only from Fugaku that is based on ARM ISA, we have seen really a resurgence of these vector processors. There are really a lot of implementations that have been done by research and companies and by ISA players. So we are not talking only about ARM, we are talking about RISC-V, we are talking about NEC that is building very, very large vector processors. And yeah, many companies, many players here, and many research institutions. And you know, like there's a reason. So vector processors we will see today, they're intrinsically efficient, let's say in terms of how they compute data. And their applications are easy to write, meaning that we know like the programming paradigm, you know, since like 30, 40 years ago. And you know, with the resurgence of AI and machine learning that are data oblivious, massively parallel, we can really massively exploit with this data level parallelism. And not only like these vector processors that were confined in HPC for HPC applications now kind of escaped the cage of HPC thanks to machine learning algorithms that are also used in IoT applications at the very edge. But first, let's try to understand why bothering at all with vector processors. So, you know, we have scalar processors and we have learned how to exploit instruction level parallelism. Why isn't this enough? So let's start for this very simple example. Forgive me for how simple is this, but now we just need to accumulate a multiplication of elements of a vector. So we just need to do a vector product. And you know, this C kernel, this C loop is translated into some assembly instructions that will be executed by the scalar core, right? Let's see why this is not efficient. So we start loading the vector elements in the loop. And for the first element, one instruction to load the first element A. Then one instruction to load the element B. Then we can start doing the computation, which is the only thing we really care about, right? One instruction to compute the multiply and accumulate. Then we need to bump all the pointer. One instruction to bump the pointer. One instruction to bump the pointer. One instruction for the index. One instruction for the branch. And you can see that we are easily 7 instructions for just one useful computation, right? This is not efficient at all. So scalar processors are super flexible. You can run everything on them, but like this comes with a cost, right? A cost in area on the left, but I want you to focus on this cost on the right. This is like the energy consumption, like for every instruction, also for the computational one, like way more than 10% of the energy is just like to fetch from the cache, right, from the instruction cache. So, for example, taking CVA6, one of our in-house RISC-V cores, we want to run a dot product kernel. Like 9% of the energy that we are actually spending for the for the entire kernel, for the entire program in the end, will go in the computation. So we want to do a task, and we just like deliver 9% of the energy to the task. This is like a great limitation of these architectures that massively need to access memory for instruction and for data movements. So this energy is totally wasted for fetching the instruction from the instruction cache, decoding them, and issuing them to the backend, right? So the intuition to start to do something better is why having one single instruction for every computation that we need, for every operation that we need, if we know the pattern of the computation. So we are computing on vectors, right? So why not doing one instruction that can trigger already the computation on the pattern that we already know of the data? So one instruction, for example, the load, but this load will start loading all the data that we want from the vector, right? So this is called single instruction multiple data, SIMD. We will see also this afterwards. But this is like the intuition behind how we can get more efficient through vector processing. So first misconception about vector processing, we said one instruction, multiple data. This doesn't mean that we need to fetch all the data at once in just one cycle, right? So with we can have an architecture that exploits SIMD parallelism in space, and this means that with one instruction, we can fetch multiple data from the cache, for example, or operate on multiple data from our register file in our FPUs, all in one cycle. And this is a kind of SIMD approach unrolled in space, right? We are exploiting the space dimension. But vector processing is not just this. So vector processors, especially, exploit single instruction multiple data, but they multiplex it in time. So you can think of this of happening in cycle 0, this data loading in cycle 1, cycle 2, and cycle 3, right? So we can also need 4 cycles with one instruction. The important thing is that we don't need to fetch instructions for every data that we're fetching. Like we will see ARA today, our processor that we will try to run processes on. Like this is a kind of exploiting both, so both in space and time. So in cycle 0, for example, is loading 2 elements. In cycle 1 is loading other 2 elements, right? A mixed space and time approach. But the important thing is that you don't restrict yourself in thinking that SIMD is just this. One instruction, let's fetch everything together. This is one kind of processors. Today, we will focus on this. So I have not talked about vector ISA already, but let's just start doing something also on C. You know, I was talking about easy, simple for loops to vectorize. So if we need to do a vector addition, scalar code, we can compile it, and we will. And we will see that this is compiled in a loop of instruction. While with a vector code, we can have like fewer instruction if we can host all the 64 elements in our vector register file. We just set up we can just load our vector elements and store them. You can see the parallelism between the scalar code and vector code. Instead of loading them in a loop, we can just load them once and starting the loading and the storing of all the elements that we want. Addition, same thing, but again, we are outside the loop. And then instead of this loop, we have just one vset vector length instruction, which is a configuration instruction with which we are telling our architecture, hey, we will operate on 64 elements. So, you know, all the next operations, you should do them and repeat them for 64 times on a known pattern. So just to understand what this means, we can start having a hands-on example. So for those of you that were not connected before we started, this is the repository that you need to clone if you want to participate in the hands-on experiences of this hackathon. So it's just like on Pulp platform, you will easily find the ARA repository. You need to check out this branch, otherwise you will not find the exercises. So check out this branch in this repository. I will now also do it with you live. And we will try to understand how scalar code and vector code differ when they're compiled for a very, very easy program like a vector addition. So just, I didn't try this before, so just tell me if you can see my screen now. Do you see it? Can you read?
Yes.
Nice, okay, perfect. So if you have checked out the MP Arathon branch, you should also have a README inside, and with a paragraph called Arathon Special. In Arathon Special, you will find the RISC-V specification that also contain the V ISA specifications. And I will just repeat this quickly. So the external people will need, so everyone will be able to write code and complete the exercises. But if you want to compile them, you need to install the tool chains. And if you need to simulate them and use printf, for example, you will need very later. Instead, for internal ISS people, you will be able to do this just by soft linking what I've already installed for you. Then you can install the hardware dependencies. Everything is written on the README. And then we will be able to compile, inspect, and simulate an application. So since this is the first guided exercise, I will just like stop for 2 or 3 minutes just for the internal people to be able to soft link everything and to follow the README. Just let me know if there are problems. And then check out the hardware dependencies. So let's do this together. So we can clone the repository. In the repository, we can check out the Arathon branch. And we can soft link all the tools. So what we are doing here is just like having ready compilers to compile from C programs to binaries that can be simulated and inspected. And then downloading all the dependencies that are used by ARA, because in this repository, it will only find the source, the system Verilog code base of ARA. ARA also uses some other dependencies like the CVA6 scalar core or AXI to reach memory through a crossbar, for example, the FPU, and you need to download them using Bender. Everything is handled and it should be transparent to you using these make commands. Okay, so while it's downloading, we can see from the README. I have prepared for you some facility to compile and build the programs for the Arathon. So we will go in the Arathon in apps. So in apps Arathon, you will find this main C, exercise and solution. I would suggest you not to look at the solution immediately, but try to do the exercise like live with me while we're doing them. Like the main code is just like a wrapper that is calling all the exercises. What you are interested in is this X folder. And for every exercise, like now we are doing the VIAD exercise. So we will just open the VIAD exercise and we can complete it. So for this VIAD exercise, I just want you to write a simple kernel, very easy, just to make you remember how to write things in C. Just a scalar addition between A and B vector to create the C vector. Here I've already written with you some vector code that should do exactly the same thing. Okay, way better. So we can just like loop through the whole vector and add it together. So once we have this, we can try to, oh, that's a big screen. We can try to compile it. With this command, everything should work out of the box if you have soft linked everything correctly, or if you haven't installed the toolchains. So let's have a look now at how this code is compiled. So we have this VIAD scalar function. I don't know if you see maybe you can see this a bit better. Yeah. So we have this VIAD scalar function that is adding two vector with a scalar core, and this VIAD vector function that is adding them through the vector ISA, right? So these vectors are just 8 element vectors. So we expect 16 loads. So 12 loads and 4 loads are 16 loads. So 16 instructions for loading. Then 4 and 4 instructions, so 8 instructions for addition and 8 instructions for storing back the results, right? This was unrolled by the compiler. You can see all the instructions that are required by the scalar execution, right? While with the vector execution, you can see that we just need this instruction to set up the vector length. So we are basically loading 8, the length of the vector in 8.0. And then we can give 8.0 to this setup instruction. So we are telling the architecture, hey, we want to work on vectors that have 8 elements now. And then we can start like issuing vector instruction, vector load, and those are sufficient to load all the 8 and 8 vector of vector A and vector B. Then we can just issue a vector add, and this will be enough to compute on all the vector elements, and then vector store to store back everything to memory, right? So you can also have a look by yourself. Now we can go on with the Arathon, but have a look by yourself. The source code is in apps, Arathon, if you want to play with it, and all the disassembly that is already automatically disassembled for you is in apps, bin, and then arathon.dump. You can then look for the functions that you have written with your source code. If you have never tried it, it's quite easy. So you have two functions, add scalar and add vector. You can just look in the disassembly for your two functions, add scalar and add vector. Okay, so let's continue. With the Arathon, and let me know also from online if you have problems in compiling or in understanding where the stuff is. Everything's good up to now? Yes. Okay. Okay, so just wanted to say again and remind you what kind of parallelism we are talking about. So just very quickly, you have maybe heard of a lot of tricks when designing processors to try to exploit different level of parallelisms and speed up the execution. Instruction level parallelisms just means that we are trying in our core at compile time or at runtime to execute as many instructions as possible in parallel. But we still have all the instructions. So one instruction for one data, for example, if we have only instruction level parallelism. Then we have thread level parallelism, right? Like the easiest thing to think of is multi-core, right? So with multi-core, we have different cores that are just executing different instructions. So we can parallelize this way. Or what we will focus on today, if we have and we need a pattern, a known pattern, so for example, a vector or matrices or something, then we can exploit it because we know the pattern in advance. So we can, with just one instruction, operate on all the data that respect this pattern. So, all this kind of level of parallelism is also useful for you to understand, like, where, for example, GPUs fit in. So, everything changes depending on the level of parallelism that we are exploiting and also how we find them. For example, there are these very long instruction word processors that will find the parallelism in the instructions at compile time. So the compiler just unroll and find all the instructions that can be run in parallel, and the processor will be fed with this, right? While superscalar and out of order execution, super pipelining in superscalar cores, these are like compiled with normal compilers, and they find the parallelism through the instruction at compile time. While what we will do today is like data level parallelism, again, expressed at compile time, because you need to remember that we need to know the pattern in advance. And this is a basic way to have efficient computation. We know the pattern well, we can exploit and we can leverage this knowledge. While the GPUs kind of also exploit the data level parallelism, but using also the thread level parallelism. So they discover this data level parallelism kind of at runtime with some clever scheduling and some clever issuer at runtime. And this also costs more power. So the message is that if you know the pattern, SIMD and vector processor will be very efficient if you can stick to that pattern. Okay, so single instruction, multiple data. As we said before, it's not only exploited in time, we can exploit it also in space. So we have this kind of duality. We have this array or SIMD processor that operate in space. So they parallelize in space, and with one instruction, they fetch in one cycle, for example, 4 different elements from the memory. So they have these white buses on which they operate. Or vector processors that we were saying before, they parallelize also in time. So one instruction triggers operations on elements in multiple cycles. And today, this hybrid approach is the most common that we can find. So parallelizing in space, array processors, we have this kind of architecture. So if we want to load, add, multiply, and then store vectors, we just start loading it in cycle 0, for example. We load all 4 elements at once, right? So that in cycle 1, we can add them at once, multiply them at once, and store them at once. So always one instruction, multiple data, but parallelized in space, right? You can see that in one cycle, we are parallelizing in space. While with vector processors, we can also have just as, let's say, a scalar, taking this to the limit, we can also have just a scalar backend in the processor, and we just load one element in cycle 0. In cycle 1, we also load the next element of the vector, and we have the element 0 already in the vector register, so we can start adding it. And then we can start multiplying the other element in cycle 2, and so on, right? So this is a kind of scalar, but we can parallelize in time. So you can see that in a single cycle, there are like multiple instructions in the pipeline. This is also basically what you can have if you have a very long pipeline. So parallelizing in time, parallelizing in space. 2 extremes. As I was saying, what we will focus on today, like ARA, is a mixture of the two. So in cycle 0, for example, we start loading 2 elements, right? In cycle 1, we load the next 2 elements, but the previous 2 elements that were loaded can already be added in the next cycle, and so on, right? So we parallelize in space and time. So this is just like a summary slide on what we can expect from a SIMD core that parallelizes in space and from a vector core that parallelizes in time and space in terms of energy efficiency. So scalar core, as we have said 3 times already, we are really putting a hard constraint on the instruction memory, and we are burning a lot of energy there because we need to fetch a lot of instructions, right? And this also requires memory bandwidth, right? While with a SIMD core or a vector core, there is a lower requirements here on the bandwidth. Something that I don't say yet is that another great advantage of using SIMD or vector processor is in their vector register file. So, register files are usually very small for scalar cores, and this does not allow you to exploit the data reuse that some application can exhibit, like matrix multiplication, close to your floating point units, for example. But with a larger register file, like SIMD core and vector core can give you, well, you have a way larger register file, and matrix multiplication, for example, the larger the tile you can have, the better is your arithmetic intensity, so you can have more data reuse. So also, this in the end translates also in lower bandwidth on the data memory.
I have a question. Before, when you show the pipeline on the vector processor, and also, so is it possible for ARA to do addition and multiplication in the same cycle?
Correct, yeah.
Okay.
Yeah, we will also see this afterwards. This is called vector chaining, which is basically like having multiple operand units. You see this, for example, this adder here, this multiplier here, store unit and load unit, they can all work in parallel, provided that dependencies are respected. And something cool about vector that we will also stress a bit later is that you know that all the elements in a vector are independent, so do not have dependencies in the same vector, in the same instruction, right? And different instruction have this kind of nice property that, you know, if you have already processed the element 0 and 1, for example, you can process them also in the next cycle because they are already processed. So you can kind of forward them or chain them in vector jargon to the next operand, the next functional unit.
And I'm sorry, it's not really on the topic, but those paths work the same way?
Yes, 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 yes.
I have a small follow-up question.
Yeah.
Does the programmer need to be aware of data dependency?
No, so this is transparent to the programmer. It's just like a hardware trick to speed up the execution and yeah, to overlap the execution also in space on different units. So in the same cycle, you have different units that are working at the same time on different data elements, but the programmer doesn't need to know anything. Yeah.
And another one,
yeah.
Is this related to the lane, or I mean, yeah, I suppose we're going to talk about lanes after.
It's not strictly related to lanes because lanes are more like sorry, lanes are more like this. Let me just erase this. Yes, you can think of lane 0 and lane 1. This is also in lane 0. This is also in lane 1. So for example, one lane has a adder and multiplier. The other lane has an adder and multiplier, and they just work in parallel. So they provide this spatial locality. So this is happening in lane 0. This is happening in lane 1. But the fact that you are also operating on the load unit that can be also outside of the lanes, it just matters that this is another unit that can work in parallel. Yeah. So you have parallelism on the same instruction through the lanes, while parallelisms on different instruction through different units.
And I have a last question. If you're going to cover it after, we can also pass. At the end of the, if you reach the end of your exercise and you need to loop, does the pipeline stall or does it continue? Yeah, this is a hardware implementation detail. So if you've done the things right, it shouldn't stall for long because you should have already in your pipeline the next instruction so that you will be able to execute. So ideally here, you can start loading, for example, load some other, vload. If this is a loop, you have iteration 0, then you have iteration 1, for example. So this vload here can already start as soon as there is no structural hazard on the load unit. Yeah. Any other questions on this? Any other last questions on this? Okay. So yeah. So yeah, between scalar and SIMD core, less constraint on the and less usage of the bandwidth, both on the memory instruction and data memory. But something cool that can be an advantage only of vector cores if we compare them to pure space arrays in the cores is that in vector cores, since we are also parallelizing in time, so one instruction can also trigger the computation on the same register for multiple cycles, well, you have way more freedom in your vector register file because the size of the vector register file is independent on the data path width. So you can have a very big vector register file, right? And then have your data path that is just a fraction of it, because then you will, for example, finish the execution on one vector register in 4 cycles, right? So in cycle 1, you will process this guy here. In cycle 2, you will be able to process this, then this, and this in time, right? So you are kind of free of selecting a smaller data path and a larger vector register file. Selecting a larger vector register file means that with one instruction, you are amortizing the cost of this instruction on a lot of cycles more, right? So the important part is also the ratio between the vector register width and the data path width. It's called the time length. And this gives you like in simple terms, how many cycles your single vector operation will last. So as a consequence, if with fixed space SIMD ISAs, you process 4 elements at a time, and you want a new ISA also supporting longer vectors, you need also to extend the ISA and have instructions that process more bits, right? And this is kind of inflexible because when you change architecture, you need to recompile with a new ISA, right? While with vector code, we will see also afterwards, like we don't care, like the software really doesn't care a lot about the length of the vector processor. This is just a hardware detail. It's transparent to software. So when you compile the vector code once, it should work with all the vector architectures on Earth that are compliant with the same ISA. Okay, so let's have just some practical intuition and understanding of how vector instruction work in practice. So we have some vector elements that we want to process, and we have our trusted memory here and our vector here kept in memory. And we have our vector core, and we can, this is RISC-V. So every time we always need to bring the data to our internal register file and then operate between the register file, functional unit, register file, right? To do some arithmetic operations. So what we can do here is starting from loading the vector to the vector register file. So we will usually load vector elements to the vector register file, and this vector register file will buffer these elements, and you can think of this as the very bottom of our memory hierarchy, right? And this is a bit easier to understand with scalar core because this is really sometimes a memory. In ARA is implemented with SRAM banks, just to make you understand that it's very, very big. And yeah, as we were saying before, as Cyril was saying, we can also be not able to process everything because maybe our vector register file can only host 4 elements. Then we will, in software, just like in a for loop, process the first 4 elements, and then we will process we will load the second elements in a second time with a different instruction. I just want you to know, I will stress this later again, if the vector register can host 4 elements, we will be able to, with one vload, we will be able to load 4 elements, right? But then the amount of instruction, so the amount of operation that we will be able to process also internally will also be always 4, right? So also with VAD, we will be able to process these 4 elements, right? This doesn't mean, as we said, that the data path processes the 4 elements only once. One instruction will just trigger the operation on 4 elements, but maybe this will be executed in 2 cycles, okay? So, okay, so we load the elements in the vector register file, and then we can start processing them until and we can load one chunk, the other chunk, until we have all the chunks in our vector register file. So just to make you understand this, the data flow you can expect also in ARA is a memory vector processor. We will start with one instruction only. We will start loading the vector. In 4 cycles, for example, we can load 8 elements, right? And a bit more in detail, we will have a load unit that is basically taking these elements with a write, with a port, with a parallelism, in this case of 2 elements per cycle, and we are writing those elements in the vector register file, right? Then let's suppose that we have loaded 2 vectors in our vector register file. Then with one instruction, we can start triggering the execution on all these elements. Let's suppose that our data path allows us to fetch 4 elements at a time per vector. So we will fetch these 4 elements first, and we will write them back in one cycle. This is without any pipelining in the processor, but let's suppose that in one cycle we can write it back And then in the second cycle, we can write it back. We can write back the second half of the vector. So in 2 cycles, in this case, we've processed these 2 elements of 8 elements, these 2 vectors of 8 elements each. And then we can expect to store this vector back in memory. So again, in 4 cycle, we can store all the result vector in memory. So the data flow is memory vector register file unit, functional units, and then back to memory. So a question that you can think of right now is, okay, so I say that the software is kind of independent of the vector length, but how can we know the vector length in software? So what we need to know is the total length of the vector in memory. So in memory, we have a vector that we want to process that have 1K elements, right? And this is called the application vector length. So the vector length in our application. So we can tell the application vector length to our architecture. So let's say that this is 1K element, and with one instruction, we can tell our architecture, hey, now we want to process 1K elements, right? The architecture, the vector core, can answer back in software, telling us which is the maximum number of elements that is able to process, right? So it will tell us, hey, I can handle maximum 8 elements. So in software, we can save in a variable this answer. So we will know that we will process 8 elements at a time, right? So let's suppose that we have this 17 elements vector. So a bit better than our 1K vector. We just have these 17 elements, and we can only process 8 elements at a time because of our vector register file, right? So we will give this information, the application vector length 17, we'll give it to this vector configuration instruction that is processed by the architecture, and the architecture will answer back saying, hey, for example, if each vector reg can host 32 elements, it will tell, okay, I can process all your 17 elements. But in our case, since we can process only 8 elements at a time, it will save in VL 8. Hey, I can process only 8 elements now. So we know in software which is the vector length of that we can process. Then we can start issuing vector operations. So let's have a brief look at which kind of operations we can, which kind of a vector magic we can perform. So, you know, load and store instruction, vector memory operation, we have plenty of them to adjust to the different patterns that we can be interested in. For example, you know, unit stride elements just means that we want to load elements that are sequentially stored in memory, right? So unit stride contiguous block of information in memory, and this is very easy to parallelize. We can just like access a wide port in memory and take everything back. If you're using AXI, we can use a burst. So you can think of whatever you can think of, but we can speed this up very easily. Then we have non-unit stride. This means, for example, let's fetch all the even indexed elements of a vector, or we can have a stride of 3, 4, 6 elements, whatever. These are a bit harder to optimize, you know, because you need to fetch different elements from the memory. Even if your memory is banked, you can incur bank conflicts if your stride is not really a friendly stride. And then we have indexed memory operation that in the jargon are called gather and scatter operations, which means that we can load pseudo-random elements from the memory, meaning that we have a vector containing the indices that we are interested in, and starting from this vector, the load unit will load the correct elements. I cannot draw. So we can also, this is increasing a bit the complexity of the operation, right? Because every index can be different, can be the same, and we need to calculate it in the vector processor. So just an example of why these scatter-gather operations can be useful. Let's suppose that we have our usual vector sum, but we can see that it's not that usual anymore, right? Because like one of the vectors that we want to load is not indexed with the I index, not with a sequential index, but it's indexed through another vector. So we have a vector D that contains, for example, hey, fetch from index 1, then from index 28, then from index 2, right? And this is like the D vector. And we need all these guys here to be able to perform the load. So we can first fetch the D vector, and this is just sequential in memory, super easy. And then when we have it in the vector register file, we can use the D vector containing the indices to fetch the C vector, using the information that we can fetch from the D vector, using the indices in the D vector. And then we can do everything else as expected. So the only particular stuff that we are using is this usage of the VD vector in this index to perform this gather operation. Okay, so some other interesting stuff that we can do with a vector. If you're falling asleep, just bear with me with these 2 slides, because then we write some code. It's like this is kind of an old problem, how to compute this kind of conditional execution in vector, because with vector we can parallelize everything if we know the pattern, if the pattern is easy. But what if we want to do our usual addition of 2 vectors, but we want only to add the elements element-wise if the element of the A vector for that index is greater than the B element for that vector. Like so in a scalar, we would just need to check for every element if that element is greater than. In vector, how can we parallelize it? Well, we use what's called the predicated execution, or in RISC-V jargon, like we use a set of masks. So the idea behind this is that if we want to load and add these 2 vectors together, and we want to add only, for example, this element because 10 is greater than 9, this element because 52 is greater than 37, and so on, only on these elements over here, well, we can also first create a mask vector that will have 1 bit only in the positions that we really need to perform computation on, right? So we will first create this kind of mask bit, and we will parallelize this operation with a parallel vector greater than. So we just say, hey, let's perform in parallel this big comparison between these 2 vectors, and let's create this small vector with 1s every time we need to compute, and 0s where we don't need to compute, and this is the mask vector. And then we can add masked. So we add these 2 elements using the mask vector as a mask, so that we can compute the C vector only on the elements that we are interested in. And then if we want, we can store also masked, only to store the elements that we are interested in, if this can speed up the execution. So masked, just a detail, we can compute everything. This is just a hardware detail. How to implement it in hardware, we can either compute everything and then avoid writing in the vector register file if the mask is 0, or we can directly mask the elements and perform the computation at the source. So we just compute on the elements that we are interested in. Okay, so let's try again with some guided example that we can do together, this predication with mask. So you can try to follow the instructions again. The only difference is that the exercise name is not VED anymore, but is mask. So you can try to write the scalar kernel to add the vector elements only if A is greater than B. And then we can start from the VAD kernel that you can find in the VAD.c example before. And we just need to add 2 instructions to modify it. And I will add them in 2 minutes.
Okay, so we can start from the example that we had before. Now we just need to add some condition, like if AI is greater than BI. While here, we will need to add, this is guided, so you can also look at the solution, because you don't know this yet. So what we do different with respect to before is once we have loaded, we set up the vector length first, then we load the element A and element B. You can think of this as just a vector load 64-bit. And then with this is a vector mask set greater than. It means that it's setting at 1 all the element of the mask vector that is creating in bit 0, starting from the first two vectors. So from here on, bit 0 will contain the 1, 0, 1, and so on elements, like precisely it will contain it will contain 0, 1, 0, 1, 0, 1, 1, 1. Then we can add the numbers together, but to add them together, we will use like the masked version of the VAD. So we will add also this vid0.t. That means that we are using vid0 as a mask register, and we use it as true. So it means that the computation is done only when there is the 1. And then we can store our vector to memory. So right now, just to show you this, I'm also initiating the vector 2 to 0 so that we don't compute the elements in when we don't compute the elements during this masked operation, sorry. Yeah, you can also take it. The elements that are not computed contains 0. So let's just run this quickly. It's called vmask, right? Not mask, just. So if you want, we can run quickly the solution, because in the solution I've also added a printf to check all the elements that we have stored in memory. So what we expect is an addition of these two vector elements, addition that happens only when the elements of A are greater than B. So this is our expected vector at the very end. So if you want to run the solution, you can do the same, but instead of X, we will use sol for solution. Okay, and then we can try to simulate it just quickly, so we can see it with printfs and simulating using QuestaSim. If you have already validated the model, you should be able to use it with validator. Sorry, I didn't compile it with printf defined. Rookie mistake.
Okay, so I'm just printing the elements that I've stored, and you can see that the vector C exactly contains what was expected, also using the masks. Do you have any questions on this? Otherwise, we can proceed. I would say we can also have a 5-minute break. By the way, also from online, let me know if this is okay for you, like if the pace is okay, or if I'm too slow, too fast, if there's something that you want to tweak.
Hello, can you hear me? Hi,
Yeah.
Matteo. I'm Lorenzo from Italy, Chip City.
Hi, Lorenzo.
Hi. Well, actually, I wasn't on my train, so I joined at 9:30. So, but I'm keeping up, right? So I have one question for you.
Yeah.
I'm following the README in your GitHub
Yeah.
repo, right? The question is, I'm pretty simple, of course. So I'm still ramping up, right, with Ara.
Yeah.
I have all the tools installed, right, on
Yeah.
my machine, right?
Yeah.
So the question is very simple. How do I verylate Ara?
Yeah. So to verylate Ara, you just need to have Verilator installed in the install
Yeah, right.
directory as required here, and then you just go in the hardware directory, CD hardware. You need
Nice.
to verylate. You need this step. So first, okay. Before you need to also check out, make checkout in hardware to have the hardware dependencies.
All right.
Then you need to have done this at least once, otherwise it will not verylate.
All right.
And then you need to go in hardware and verylate.
All right. All right. Awesome. Yeah, I'm sorry because I mean the compilation of all the tool chains
Yeah, no,
took
it's a nightmare.
yeah, it took me one night.
Yeah, I know. I'm really sorry for your night. Not the best night work.
No, I mean, but there was a problem in the make file, and I saw there was an issue. Already opened the GitHub, and and yeah, I tried twice and I failed. Then I went to the to the
Yeah, like with
GitHub.
another operating system with other dependencies, it's a nightmare. I know. Now for
All
the
right.
reason, yeah, for internal IIS people, it's really easier.
All right, awesome. But I mean, I work it out, so I do have everything now at my hand. So yeah.
Nice.
So let's try to see if these guys work, right?
Yeah, I will also add a section in the README with all the list of all the people that managed to install the toolchains.
All
And
right,
you will
awesome.
be there.
Awesome. Okay, let's see if I can verify everything.
Yeah,
If I do have
know if no, yeah, just let me know if you can.
if I have any other questions, I will ping you for sure. Thanks. Thanks a lot.
Okay, we can start very softly, just changing topic again, so that we can do something a bit easier, just like the repository. So the repository. Now I'm super embarrassed that the CI was not passing on that branch, so I need to go main again, not to be embarrassed anymore. So ARA repository. You are working with this. You are working with a special environment that I made for the Arathon, but the README is there also on the main branch. You can find all the information to install the toolchain. For sure, as Lorenzo mentioned, you will have for sure problems in installing everything, because you will need to hammer a bit the dependencies and stuff. But once everything is installed, it should work out of the box. At least it works on my machine, as a famous quote said. So repository, you will have like many folders, but the important ones are hardware, which is basically the source code of ARA. And you have all the source code in hardware source. You can see that there are different modules, and here you can spot our best guy here, ARA, and some division in vector unit, vector load unit, and store unit, slide unit, mask unit, lane, and the content of a lane. So we also have a test bench infrastructure, and always in hardware you can find all the system Verilog modules and the wrapper for Verilator. While in apps, which is the folder that we are using massively now, you find all the applications that ARA can run, together with some external benchmarks, suits, and the RISC-V tests vendorized repository that is basically a set of tests divided by ISA. We added hours for the vector extension. You can see these are all the subgroup of instructions, and every subgroup of instruction have some dedicated tests. So this is how we test ARA, and how you can also maybe explore the vector instructions by yourself if you like. Okay, let's go on with the presentation. So now we explored how to do some masked computation, so predicated execution with masks, and we can speed up the execution and parallelize it also in presence of this if conditional branch, right? Now let's see something else that a vector processor can do. Vector reductions. Up to now we've talked about vector-to-vector operations, like element-wise operation, for example, vector additions. But with a vector processor, we can also reduce vectors to get a scalar. So this is a horizontal operation on the vector. And this operation, is just like, let's start from this VA, and let's vector reduction sum of the elements and get all the sum of all of them. You can think of this as an operation full of dependencies, right? Because we need to wait for all the other sums before being able to sum the final one. This is one of the fastest way you can do with a logarithmic tree, but you can implement it as you prefer in hardware. So now I want you to pay attention to this, because this is the heart of vector processing. We already mentioned this more than once, and this is basically, we will try to understand how to write a vector program that is independent on the vector architecture on which it's run, right? We have already seen what the problem can be. We have a very long vector to process, and our vector register file has a size that we don't know, right? Because we are running the program on an architecture that we don't know as well. So our application vector length is 143. Maybe it's even better if I don't cross it with my annotations. So something that we can do with this vsetvl configuration instruction, is query the architecture to understand what is the size of the vector register. This is not something that you would do in a real program, but it's something fun just to make you understand how this instruction works. So if you just pass to this configuration instruction 0, it will return you 0. 8, it will return you 8, and so on, until at a certain point, it will cap, and it will start returning 64 when you start increasing the application vector length. Well, this means that your vector register, that a vector register in your vector register file can host maximum 64 elements. So you can process up to 64 elements with a vector instruction. So how to process the 143 elements? Well, we split the computation in chunks and in different iterations. So instead of having a for loop with one operation per iteration, we will have a for loop with 64 operations per iteration. So we break up the loop, and if we have 143 elements to process, we first process 64 elements, then we process the next 64 elements in memory, and then we process the tail 15 elements. This is called vector strip mining, and this is exactly how you should write a vector program to make it compatible with all the possible vector architectures out there. So you will have a while loop or a for loop that is basically saying, okay, now I have this AVL that is initially the application vector length, but during the loop, I will update the application vector length, removing the elements that I've already processed. So in the beginning, we say, okay, how many elements you can process in this iteration? And the architecture tells you how many it can process. We save it in VL, so that at the end of the loop, we can remove all the elements that we have processed from the initial ones, and the while will check and continue until, well, until we have still elements to process, right? So until AVL is greater than 0. So with this strip mining loop, you are pretty sure that you can work on every architecture possible, regardless of the vector register side. So remember that you can read online or everywhere that the vector code is agnostic to the vector length. This is only true if you write strip mining loops in your software. So thing is that you don't need to write a code for 8 elements, but you need to save it in a variable. Okay, so let's try to do some strip mining. This you can do. This you can try also by yourself, just 3 or 4 minutes. You can start from the VAD exercise that we had before, and look in the exercise VAD strip mine.c. You can copy paste your VAD exercise, and you can just add the strip mining loop. I will also do it together with you. So you can start from the VAD. You can start from the VAD example that we had before. You know, this VAD example had the problem that it's not iterating in a strip mining loop. So if we need to process only 8 elements, it's fine because ARA has a longer vector register file than 8. But if we need to process, for example, 256 64-bit elements, well, ARA will process only the maximum number of elements it can process. So it will not process the whole vector if we don't implement a strip mining loop. So we will need to define application vector length, that in our case is our trusted n. And we will also need to ask for VL. So this is the syntax. I'm just writing assembly because then it's way easier to understand what's happening after the compilation. So I'm giving vsetVL. This is basically so we are saving. We are giving application vector length, and we are writing in VL the number of elements we can process with the following instructions. So we will need yeah. Let's give more space to this. So what we will need to do is having a loop that somehow is iterating until AVL is greater than 0, right? And at every time is removing the vector length. So now we have a loop, right? But what we need also to do is, so AVL is already taken care of here, right? What we need to do is also modifying the pointers, because we are also, we have a vector in memory. A, B, okay. So element 1, element 2, element 3, element 4. So if we can process, for example, the first two elements with an iteration, and we start from an address that is pointing to this first element in memory. Then in the next iteration, if we process two elements with a load, in the next iteration, we should also start and bump the address to fetch the elements from 3 on, right? So in the second iteration of the loop, we expect, keyboard. We expect to fetch element 3 and 4, but we need also to bump the address. So AI needs to be updated. By how much? We can update it by VL, so the number of 64 elements that we are processing. Same stuff for, of course, for B and C. Okay. So you can also try to run your example. In the end, you should have something like this. This is exactly what I wrote before. And with this, you can look also at the disassembly, and you should see that now okay. So if we have a look at the disassembly, we can see that we have strip mine. Scalar is always the same, but with a loop now. So scalar is now, loading two elements, adding them, storing them, bumping the pointers, and then branching back. This is the scalar loop. So we have these 8 instructions per loop, per iteration, sorry. While with the vector extension, we have a bit more operations because we need to also shift the pointers, like shift to add VL. We are not just adding one, but this is exactly the same loop, just in vector. So you can say, you have more instructions, right? Obviously not, because like this is just the static trace of the program. So this is the amount of instructions in your memory, but then every one of these instructions is working on VL elements. So in the end, we will fetch way fewer instructions with this vector program. Okay. Do you have any questions on this strip mine? Otherwise, we can proceed. So this is just to tell you, this is just exactly like the program that we have just seen with vector addition, And here, I just wanted to tell you like how powerful is the vector extension. We want to do a vector addition, integer. If we want to go floating point, you see this is the only thing that is changing. So vector floating point add. And then we can also add the vector scalar, for example. There is also an instruction for that. So vector adding a scalar in the scalar register file. So we can play with a lot of different kinds of flavors of instruction with the vector extension. Okay, so let's have a brief look at the RISC-V vector extension ISA. This is very useful for you because it's basically your cheat sheet. This is the extension. At chapter 30, you should have the V standard extension for vector operation. Yes. So, big documents of specification, even if way smaller than the ARM specification. Anyway, it seems intimidating, but it's actually pretty easy. Basically, this vector extension just defines two different constants that are called ELN and vector length. So we just define two parameters. You can also have the specifications there to check it. So we just specify the maximum size in bits of one of the vector elements and the number of bits of a single vector register of a vector register file. And these are architectural constants. Once we have this, we can implement the hardware as we want, right? Following that, there are, if you look at the summary, you can see that there are some new vector CSRs that are defined. It's defined like the vector register file byte layout. So how it should behave when we load something from memory and we process it. Then, of course, the instructions. And the instructions are just macro sets, configuration instruction, the famous vset vector length that we've just seen, memory instruction, load and stores in all the flavors possible, arithmetic instruction, integer, fixed point, and floating point related instructions. There's plenty of them. Permutation instructions, so if we want to move elements from one vector to the other, and masks instructions. So if we want to compute on masks, or if we want to compute on mask-like vectors with bits. So a bit of just like some history because it's fun. So this started in 2015 and it's 2025 now. And this is really a big ISA. We developed the ARA in 2019 here in-house in ETHZ as a prototype when the specifications were just a deck of slides. So now with ARA 2, how it was called, it should be compliant with the V1.0 specification that is also merged into main after years of modifications. Okay. Okay, just quick summary of the ISA. So the ISA is specifying that the vector register file should logically have 32 vector registers, so from V0 to V31. By the way, I hope I'm not mute. Okay, yes, just checking. Okay, from V0 to V31, VLAN, we say that it's the parameter that is telling the length in bits of every one of these vector registers. So V0 is VLAN long, V1 is VLAN long, and so on. And then vector type is one of the CSRs that is added to the vector extension. It's useful because, you know, it's a CSR, so we can program it at runtime, and we can tell the architecture that the element width of our vectors that we will be operating on is, for example, 8, 16, 32, or 64-bit. This is the width of every element of the vector. Then we can also say, okay, we have 32 vector registers, but we can also have a parameter called the length multiplier, that when is 1, well, the vector register is interpreted as you can expect. So 32 vector registers, everyone has a VLAN bit, is VLAN bit long. But when we have, for example, lmal equal to 2, it means that we are merging, for example, V0 with V1, then V2 with V3. So in the end, we will have half of the vector registers, but with twice as much the capacity, right? So we can play with the vector register in this way, and then we have the vector length that controls the number of elements that we are operating on. So, you know, the one that you are setting up with vsetVL. So this is the vector register file. You can see that is 32 vector registers. They are all VLAN bit long. This is a constant. And VLmax just means the maximum number of elements that is contained in one of the vector registers. So, you know, VLmax will be just VLAN in bits divided by the element width of every element of the vector in bit times the length multiplier if we are merging vectors. So, for example, with lmal equal to 1, we have 32 vector registers from V0 to V31. With lmal equal to 2, you know, we have only the even registers with twice as much the capacity. With lmal equal to 8, we will just have 4 mega vector registers with 8 times the capacity of one vector register file. This means that we will be able to accommodate way more and buffer way more elements per instruction. Okay, so vector unit configuration, we have tried it in the programs already. We have this vset, VL, VLI, we have many flavors of this, and we can write assembly code to set up this vset VL, and we can set up with this the vector length, we can set up the element width, so we can set up, for example, E64, E32, and so on, and the lmal parameter. In the code you see it written as M1 in the vsetVL. So with just one instruction, we can set up the element width, the vector length, and the length multiplier. Yeah. So now let's try to experiment, and this is up to you, especially if you can simulate. I know that many of you cannot simulate, so we will do it together. We can have a look at the vector register file of ARA, right? With vsetVL, we can try to see how long is the vector register file of ARA. And yeah. And how many elements we can save and how the vsetVL operate. This is the instruction to set up the things. I will just go a bit quicker in the solutions here. So since many of you cannot simulate, but if you want, you can play with this. So for example, we have our kernel, right? And we can vsetVLI, this configuration instruction, and we have This is the AVL. Sorry, the VL that is returned by the instruction. This instead is the application vector length that we are giving. Then we have the element width. And here is just like we are operating on 64-bit elements. See, standard element width. Then we have LMAL parameter. And these last two, you don't really need to care now, but it just means tail agnostic and task agnostic. It means that if we are not operating on a whole vector register, this means that we can leave the elements that we have not processed, so the tail elements of the vector, unchanged, or we can override them with 1, who cares? Another possibility is having undisturbed and undisturbed, meaning that the elements that we have are masked during a mask operation, or the elements of the tail of the vector that we are not overwriting needs to be left unchanged. So we cannot overwrite them in any way. So anyway, let's just experiment something. So to find the maximum vector length of the vector processor, you can pass as application vector length -1, because -1, you know, is just like FFFFFFF, depending on your on the length of your data type, right? But it's basically in unsigned, and this is interpreted as an unsigned. For this operation, it means maximum possible. So you will have in VL the maximum number of elements that can be processed by your architecture. Then to experiment you can experiment something cool, because you know, VSET-VL is giving you the number of elements, right? So if you are processing 64-bit elements, or you are processing 8-bit elements, you know, you will get 2 different VL. So you can expect that if this is VL, there will be 8 times the previous VL, right? Because with the same width of the vector register, we can fit way more elements with 8-bit only. So if we try to compile this.
I have a question on this.
Yeah.
If the FPU doesn't handle 8-bit SIMD, it doesn't matter. It is just in the instruction after, but
Yes. So yeah, this is more of hardware detail. So depending on how you implement it, we will also see it afterwards. Usually, for example, let's take ARA as an example. It works as in a SIMD fashion. So its FPU is capable of handling, for example, either one element of 64-bit or 4 elements of 16 bits in one cycle, right? But if your FPU does not support this SIMD fashion execution, well, then it will process one, I don't know, 16-bit element per cycle. So it will be just slower.
okay.
Yeah. So we can print VL, for example. Okay. So, for example, if we print the VL when we change the data type, so same settings, we just change working on 8-bit elements instead of 64-bit elements. The VL will also change. So let's try to compile. This is VLI. Exactly. So you can see that when we yeah, so we can see that when we use vset VLI and we have like maximum application vector length, and we ask for a 64-bit element or 8-bit elements, ARA can work on 64 elements with 64 bits or 512 elements each of 8-bit in just one register, right? Now we can also play, with the vector length multiplier. So we can do better. We can increase the number of elements that we will be processed. If, for example, we have 8-bit elements and M8, so M equal to 8, meaning that we will have only access to V0, V8, V16, and V24. And this will give us like the best, like the highest VLAN possible. Yeah, I didn't update the M, but the last one is this should be with M8, and you can see that the number of elements that we can process now with just one VAB, for example, is 4K elements, right? 4K 8-bit elements. So all the next instruction will perform computation on this number of elements. Okay, so let's come back to the presentation. Okay, so we have seen that this instruction set is kind of compact, meaning that with one instruction we can work on an operation. And what I was telling before is that this is very powerful because vector means that we are telling the hardware that, for example, all the elements in a vector during a vector instruction are independent. So if we are loading all the elements from vector A, we know that we can load them in parallel, we can load them sequentially, we can do whatever we want, because this element and this element will for sure not have any dependency, right? So if we do it, if we have enough resources to load everything in parallel, we can, who cares, right? So this is giving freedom to the hardware for menu optimization. Also, in one instruction only, beload, they will only use one functional unit, the vector load unit, for example. Something that is also important, like we know the pattern, right? So we know the pattern and we can optimize the pattern of access in the vector register file. And I don't know, unit stride is contiguous block of memory. So we can perform menu optimization in the load unit. For example, ARA uses AXI4, so we can use bursts, right? And this is a great optimization to speed up the execution. And also, non-memory pattern, so if you want to play with some clever prefetcher, bank manager, whatever, in the load store unit, we can do it. And also, it's scalable, right? Because, we can really, in hardware, we can have many lanes we want, as many pipeline stages as we want. With a long vector, we are sure that we can keep the pipeline busy for a long time. So this means that we can pipeline also our units a lot, especially like the longer the vector that we have, the more a single instruction will keep all the pipeline busy for longer, right? So even if the instruction memory experiences stalls, or the pipeline on the front end of the processor experiences stalls, and the second instruction gets a delay, for example, vector load, vector add, like we have the vector load, but the vector add is now stuck, right? It's stuck in the instruction cache. Everything is stalled, right? At a certain point, who cares? Because even with a long pipeline, the vector load will load, I don't know, 8, like we saw with ARA, 8, like 4K elements. So it will start like operating on them in multiple cycles. The pipeline will be busy for a long time, and we have all the time to get this unstuck, getting it in the front end of the vector processor. So as soon as this is the elements here are ready, we can start operating with them, right? So This is very cool, and also we can pipeline the units. We don't really care of the latency when we have long vectors. We can just care about the final throughput. Also, this is cool because pipelining means a lot of issues when we have hazards, but in a single vector we don't have hazards between elements, right? So we can have simple pipelines. Also, as we were saying before, we can implement the hardware as we prefer. We have a VHEAD. We can execute the VHEAD just with one functional unit multiplexed in time, right? So that the index 3 is processing one cycle, index 4 in another cycle, and so on. But we can also have multiple parallel lanes that performs operation on element 0, 1, 2, and 3 in just one cycle, and then another cycle 4 in parallel. You are free to do this. This is transparent to software. So what we usually do is kind of having a hierarchical structure that is a lane, and you will find this in ARA. So we kind of split the vector register file. So this is the logic vector register file. We split this vector register file, meaning that this is V0, this is V31 horizontally, right? But we split it vertically. So we have some slice. Every lane will contain a slice of every vector register from V0 to V31. And what is cool is that the lane is kind of a small scalar processor, right? Because we have a chunk of the vector register file, some vector units, maybe this and this, and the memory subsystem is connected to every chunk of the vector register file. So this provides a scalar template to be reproduced if we want to scale it up, right? And we exploit locality. So as we will see also for ARA, this guy here is small and is connected with an interconnect just one unit, instead of having a big monolithic vector register file that is connected all the functional units. And we exploit locality. So what we want to do is that element 0, for example, will be kept in lane 0, element 1 will be kept in lane 1, and they will always stay there, right? So we always try to process in the same lane, trying to minimize the movement between one lane and the next one. So this is what you were asking before. So vector operations can be trained, and this is like one of the cool parts of vector processors. In scalar cores, you have this mechanism called operand forwarding. So when you have a read after write hazard, so we first write R1, and then we need to read it with a later instruction. So this is time. To read it, we need to wait the add to write it in the register file. So you have the mul that is stuck here with a hazard because the VHEAD is still here in the pipeline. So R1, the content of R1 is now here, but the multiplier cannot take it from the vector register file, right? So what can we do in scalar core is bypass. So we just bypass the content of the R1 here, so avoiding the cycle more. In vector, we can do the same thing. It's called chaining. So we can also forward operands. For example, we are loading. We can chain the load to the multiplication if element 0 is here and element 1 is being loaded, element 0 can already be given to the multiplier so that element 0 can already be processed without really waiting for all the vectors to be completed, right? This is more similar to operand forwarding, but what we do in ARA and what it's done today, usually in vector processor, is this kind of implicit flexible chaining. This means that all the operands pass through the vector register file, which is the focal point for the chaining. So you can think of, now we will go back in time. You can think of the V multiplication. It's like, the vector addition that comes first in time and is taken from V2 and V2 and started processing right back in time. And since the multiplication needs V1, well, we can chain it, meaning that, yes, the addition writes it in the vector register file as expected. But the multiplication doesn't need to wait until the end of the addition. Since V1, 3 and the previous element, V1, 2 and V1, 1 and V1, 0 are already in the vector register file, well, it can start taking them from the vector register file, right? So this means, as you can see, that the two operations are really chained. One operation starts and the other immediately start using all the results that are already present in the vector register file. So this means that without chaining, we need to wait until the load is over to start the dependent multiplication. With chaining, we can just fetch the first chime, and then we can start using it in the next cycle in the multiplication, and so on. And you can see we are chaining the vector. So we pay, and this is one of the most important part of vector processors. Even if we have dependencies, we pay them only in the first cycle, because all the other cycles can be chained, and we are not paying this dependency in cycle per cycle. So we can start loading, loading with the load unit, this vector. This is cycle 0, cycle 1, cycle 2, so we parallelize in space and time. The multiplier can start in parallel, so the addition can also do the same. So you see that here in this cycle, sorry, well, this is not really a cycle. In this cycle here, there are three functional units that are working in parallel on different elements of the vector. The load unit is loading 8 elements. The multiplying unit is multiplying the 8 elements that were already processed. And the add unit is working also on the previous elements that were already processed by the multiplying unit. And this is cool because, as Cyril asked before, once one of the load, this is a kind of strip mining loop, right? This is the first load of a strip mining loop. This is the second iteration of the strip mining loop. We can have them back to back, right? So that in the end, you see that with just one instruction a cycle, we can perform 24 operations per cycle in parallel on different units of the processor. So let's have some hands-on again with chaining. So here we will also have a look at the waveform. Wait a sec, I was stuck in PowerPoint. So let's look at this chaining. So just to explain you chaining, we have a iteration loop here. We are just like loading some elements, adding one to each element. So this is just a scalar addition, and then storing the result back to memory, right? So what we expect is that, for example, this load and the add, so the add shouldn't wait for the load to complete the whole vector load, but can already start overlapping the execution between addition and load. So let's see. Okay, so this is ARA. There are a lot of waveforms, but you don't need to worry. I will just focus your attention on the important stuff. So we have the vector load store unit, right? Vector load unit because we want to catch when the load is performed. You see that there are we have a strip mining loop. So these you can see 4 spikes. This is the strip mining loop, and these are the 4 loads of iteration 1, iteration 2, iteration 3 of the strip mining loop, right? So you can see here that we are loading a vector, now vector of 0, so we are not loading anything interesting, but you can see that we are loading many elements per cycle here, and this is the time span in which we perform the vector load. At every cycle, you see that with one instruction, we are performing operation on many multi-clock cycles. If we go and see, so this is our load, right? If we go and see when the addition is performed, we have these 4 lanes that work all in parallel. Let's just focus on one of these lanes in the vector ALU. And we can see that the ALU starts operating with valid I already during the load. So you can see that the vector load starts performing operations during the load. So initially, the elements that are taken in this cycle, for example, are the first ones that were already loaded, went into the vector register file, and dispatched to the ALU of the units. So instead of waiting this time plus this time, we are overlapping, and the overhead is just some like five clock cycles. And we can see that afterwards we need to store every time. Just small curiosity, you see that we store from here, so we overlap also the store and partially the vector addition. Why can't we start before with the store? Because load and store are serialized with one single memory bus, so there is a structural hazard. The load needs to finish before we can start with the store, right? So anyway, this is our full load and add overlapped, and then store partially overlapped. And here we have our strip mining single iteration. You can see that the next load is started some cycle after. This is just inefficiency. Like if we want, we can also try to push the start of the next load a bit more closer to the store with an optimization. And then we start the other iterations. Okay. We can have a brief break. Also, if you want to try with the chaining, and then we will start talking Ara. If you have questions, you can directly ask me. In the meantime, I can show you if you want something. So this is our friendly load. This is our friendly store. Not this. This. You can see here the overlap. And just to show you also from the other lanes, the same thing is happening in parallel. So these are the 4 lanes that operate in parallel. And you can expect the 4th lane to do exactly the same.
Is there a valid signal then that the result is valid?
This is just like to show you when the valid input are valid, but this, for example, we can also see when it's written in the vector register file. Signal, for example. This is the grant from the vector register file of lane 0. You can see that it's pretty much the same. So it's just like delayed by 1 cycle.
No, but I mean, if I want to see how many cycles it takes to execute a program? What's the
Okay, so here in this case, for example, we can also do it with a counter in software, but in this case, so this is the whole iteration loop. So this is the last cycle in which R is storing.
and if use this active write valid?
Yeah, so this is just a simplification because if you want to see when everything is over, you can take the B channel of AXI when it's valid and ready, which is exactly this moment. So here, everything has been written to memory with the final store, for example.
What's the B channel?
So AXI is a protocol that is composed of 5 different channels. With 2 channels, we just say, we just transfer the address. With 2 channels, we either transfer the data that we want to write or we receive the data that we read. The B channel is just saying, after a store to memory, it's just saying everything you wanted to store has been stored. So it's basically saying, I'm over, I finished.
And it happens at the end of the program?
No, it happens at the end. So for example, when we want to store all the elements with a vector store, we start IXI burst. That just means that we will provide elements to the memory. For example, we provide 64 elements in multiple cycles, right? And the memory just tells us once the last element has been written in memory. So you see that we have 4 different vector store. We have also 4 different be valid from memory. Since we know that this is the end of the program, so it's the last thing that the vector program is doing. I was just showing you that the whole program is taking from the first instruction that has been dispatched. This is the first instruction that has been dispatched, oops, to the very last B channel response. But if you want to know how long the program was, you can also do it in software using some counters. So for example, you have some facilities like start timer and stop timer before and after the program, so that in the end, get timer will give you the amount of cycles spent between start timer and stop timer. Okay, we can go on. With a bit of Ara. Is this still recording? Yes. Okay, so let's now have a look at Ara. So we have seen how the vector processors behave. Now, Ara is our architecture, is the architecture on which we have simulated. So it's important to understand. So Ara is a decoupled architecture, vector architecture. That means that Ara per se is just a vector accelerator, but cannot access the instruction memory. So it needs to be coupled with a scalar core, CVA6. So CVA6 and Ara are coupled. Ara is the vector accelerator, and both have private data memory ports. So you can see that CVA6 also have a data cache and goes to memory, to the second level of the memory hierarchy through an AXI crossbar. Ara does the same. So Ara directly accesses the level 2 of the memory by passing CVA6's cache, and they all use AXI protocol. So Ara is a lane-based design, as we have seen before. So we have a lane that contains also a chunk of the vector register file, and every lane contains one FPU and one ALU. And this is like the small template that we can reproduce. So Ara is modular and scalable from and can scale from 2 to 16 lanes. You can also scale it more, but then it's hard to implement physically. So double the lanes means double the maximum performance. So every lane has one FPU, since one FPU can compute one MAC a cycle, and one MAC is multiply and accumulate, so 2 ops a cycle. And these are double precision ops, so on 64-bit. It means that every lane, this is like a cycle per lane. So every lane increases the performance by 2 double precision operation per cycle. So with 8 lanes, we can expect a maximum performance possible of 16 double precision floating point operation per cycle if we are using multiply and accumulate. Okay, let's just see how ARA can be built. So we start from CVA6, the scalar core, and we need it to fetch instructions from memory. And then we can add the vector unit, ARA. We have said that they both access the memory with a private road store unit. We also add the memory interconnect. And we said that we have a parametric number of lanes. So every lane can instantiate a chunk of the vector register file to buffer the operand within the lane, and an FPU and an ALU. This is just a zoom on the lane. And the lane, you can think of computational heart of ARA. So every lane has a chunk of the vector register file. So vector register file chunk, and ALU, and a floating point unit, right? And then some control to fetch the operands, redirect them, buffer them, operand queues. We will see them more in detail afterwards. But you need to know that the parallelism of every unit in the lane is 64-bit. So this is what happens inside of a lane. We will see it again afterwards from a different perspective, but you need to think that every lane is a chunk. Every lane in the default configuration has 4 KB of vector register file chunk, and this is a lot, and it's implemented with SRAM memory. So every chunk in every lane is physically composed of 8 SRAM banks. Every bank has one write or read port, and all these banks are connected with an interconnect, 2 buffers that are called operand queues, and will give the operands and buffer the operands for the functional units. So we have this system that has also, we need some more interfaces. So this is just to say that there are more interfaces here. We will see the interface one by one. So let's just see how like the instruction flow works. You know, CVA6 can fetch instruction from memory. The instruction can be either scalar or vector. If it's a scalar instruction, we execute everything in CVA6. If it's a vector instruction, we partially decode it, so the CVA6 knows that it should be dispatched to ARA, and then we dispatch it to ARA. The dispatch happens when the instruction is non-speculative anymore. So, you know, CVA6 has a scoreboard to manage dependencies, meaning that all the instructions are in a, let's say you can think of it as a FIFO. All the instructions go down, let's say they go up and reach the top of the scoreboard when they are not speculative and when they can be committed. So when the vector instruction reaches the top of the scoreboard, from the point of view of CVA6, it's fine, it's legal, it can be dispatched. So ARA will just answers back saying, hey, there is no exception. There is no exception on this instruction, so that CVA6 can commit it, since from its point of view was already okay. So CVA6 can continue outstandingly to fetch other instructions, while ARA, in the meantime, is executing the vector instruction. So thing is, the vector instruction can be executed only if there were no exceptions, right? Many of the vector instructions, for many of the vector instruction, we know already at the code time if they can generate an exception or not. So ARA is composed of different modules. The first one, for historical reason, is called dispatcher. This will be renamed, I think, because it's just a decoder plus the vector CSRs that we have seen before. So the instruction is given by CVA6, is decoded here. It's just a big case system Verilog block that decodes the instructions and creates the control signals to be given to the sequencer that contains the vector scoreboard to manage the dependencies. We will see this in more in details, and also assigns the hazards bits to the instruction if needed, and then broadcast the instruction to all the different units. And each unit will take the instruction and get the instruction only if it's a related one. So we have different units, the vector load store unit, address generator that is handling the AR and AW channel of XE. So it's creating and setting up bursts, for example. Then the load unit is getting the AXI bus, and the vector store unit, the W, so the data to write, and the B, the famous B signal saying, yeah, everything is done. So then we have a slide unit to perform permutations, meaning we need to move elements from different vector register file chunks. So we need the elements from all the lanes. We need to shuffle them and then store them back in the lanes. And then we have the mask unit to perform the bit masking, the ones that we played on before. And then our lanes. So this is the architectures in pulp colors. So, scalar execution, vector execution, we really liked. This is a bit more complete one if you want, where is the reduction support, exception handling and stuff. Now let's see again, this I've already said, this is from, let's say, from another perspective. I will be quick, but just for you to really be on the same page on this. The vector register file is large, have 32 vector registers, but it's split into lanes, right? So we have 1 kbit per lane, and in every lane, we physically implement the vector register file chunk with 8 different SRAM banks. So every lane has this, right? And these banks are all connected, should be connected and should feed the functional units in every lane. So here we are into the lane. We have a ALU, a multiplier, a floating point unit. To feed them, we need a crossbar and some operand queues that are just FIFOs feeding the functional unit in the lane. And then we also have, we also need to provide the operands to the external mask unit, slide unit, and load store unit. And this is cool because, if we can stay here without slide unit, we can leverage the locality. So same index stays in the same lane. So every lane, you see, have its own chunk of the vector register file with 8 banks. If we want to load from memory, this was a bit messed up. But if we load from memory, we pass from and to the slide unit. We get the elements from all the lanes, and we can load and store them. If we want to load, we load consecutive elements in consecutive lane. We'll see this afterwards. So element 1 in lane 0, element 0 in lane 0, element 1 in lane 1, and so on. And then we wrap up. If we want to shuffle some elements, well, we need to also move elements among lanes. So we first give the elements to the slide unit so that the slide unit is able to write the elements back into different lanes. So the elements first go to the slide unit and the slide unit writes back. Same stuff for the mask unit. We want to support the bit masks. So first we need to give the mask vectors to the mask unit so that it can create the byte strobe starting from the mask bits and give to the unit saying, okay, next byte you shouldn't need to process, next byte you need to process. Okay, so vector length and everything can change at runtime with set VLI. So if we are loading a 64-bit elements, you remember consecutive elements in consecutive lanes. So this first 64-bit element 0 will all go in lane 0. But if we are loading a vector of 8-bit elements, for example, we will have that first byte will go, first element, which is also first byte, will go to lane 0. Second byte, that is second element, will go to lane 1. So different elements have different byte layout mapping in the different lanes. Expensive, that means expensive interconnects. Okay, now let's have a look at the high-level architecture of ARA. So let's step back and see how is interfaced to the memory and to CVA6. So, you know, CVA6 needs to provide instructions to ARA, the vector instructions. So we have a request interface in which we just say, hey, ARA, I have a valid request, and I forward the instruction. So this is really the 32-bit instruction. Then if you need some elements from the SCADA register file from CVA6, I will also give it to you, and then just a transaction ID to get also the answer back from ARA, and a rounding mode for floating point operations. And this is answered back by ARA. So just request and response interface. Then we have a memory interface. So CVA6 and ARA has these AXI memory ports. And the thing is that ARA goes into the lane with a wide memory port that is proportional to the number of lanes, while CVA6 needs a bump, since right now has a bus, refilling bus for the L1 data cache that can also be lower than the number of lanes times 32-bit. For example, with 8 lanes, this is 256, and this is 256. So this also needs an upsizer. Okay, something also interesting is that ARA is entering the memory with a 256-bit parallel AXI bus. So you can also instantiate a non-banked memory, because we are just going there in parallel with our wide port, and this simplifies the interconnect, because we don't have many small ports that need to be rerouted. Okay, before stepping into the coherence problem, let's have another 2 or 3 minutes break so that I can drink. And then we can go on. Okay, I think we can go on and so continue like with like follow up with this. That is basically. By the way, do you hear me from online?
Yes, we can hear you.
Okay. Okay. So let's try to understand, since we have two different load store units, let's try to understand how to deal with coherence and consistency, and the consistency model of like mandated by RISC-V, and also like what you would expect with program order. Even if we have only one core that is fetching the program flow, we have two load store units. So in terms of coherence, we have a problem because the memory hierarchy is different from CVA6 and ARA. So what if CVA6 stores to address, and then ARA load from the same address, right? ARA is reading the stale data. So the solution is to use to force a write-through cache on CVA6, so that when CVA6 stores, also ARA will load the same data, right? Then problem like other way around, if we store with ARA, how can we load data from CVA6 without violating coherence? Solution, we need to invalidate the stale data in L1 data cache. So the W bus of the EXI in ARA is snooped on by this invalidation filter that can invalidate all the sets that are written to by ARA. So ARA is writing in the L2 cache or L2 level of the memory hierarchy, and this invalidation filter can clean up and wipe all the related sets, so that CVA6 will need to fetch again from memory to perform the load, and we'll get the OK data. Now, we also have another problem, more of in terms of consistency and memory ordering and read after writes in memory. So how to order vector loads with respect to scalar loads. Okay, the solution is just that this is not really a problem because of the relaxed memory consistency model of RISC-V. So we can also, if we don't respect the ordering of these loads and we don't have atomic operations, this is fine. But what if we are now ordering, we need to order vector load and scalar stores, right? So the problem is that if they are storing, if CVA6 is storing to the same address that ARA is loading from, and this we don't know, right? Because we have two different load store unit, and CVA6 is not really decoding the instruction, just forwarding it to ARA. The solution that we came up is just like if there is a store after a vector load, so we have this. So we have a scalar store after a vector load. We will block the store in CVA6 until there is a pending vector load. So as soon as there is no pending vector load, so the load is completed, the store can be dispatched to a CVA6 load store unit and can start, so that we are sure not to overwrite, so this write after read hazard, right? If there is a load, vload after a vstore, so this thing here, we will just dispatch the store to the load to ARA. So we dispatch the vector load to ARA, but the vector load will wait until there is a pending scalar store. So as soon as there is the pending scalar store is over, so the store has been done already in write through, then ARA will be able to start the AR transaction on the AXI AR bus. So we're basically forcing the ordering of the scalar load and scalar stores, and this is also what happens between vector stores and scalar load. So load following vector stores, we issue the load in CVA6 only if there is no pending VStore anymore. So we wait and we serialize the two operations, the issue of the load until the store is over. If there is a vector store after a scalar load, this is already ordered and serialized by CVA6 scoreboard, because the vector store to be dispatched to ARA should reach the top of the scoreboard. And for this to happen, the load should already have left and commit the scoreboard and being committed by CVA6. So the load was already done and performed by CVA6. So how to order a scalar store and vector store instead? Same thing as before. We issue the scalar store only if there are no pending vector store, or we issue the vector store to ARA, but we start it only if there is no pending scalar store. So basically, to summarize, we are forcing a serialization to ensure that we can not run into read after write in memory. So we added this coherence interface with the invalidation. So we just have in CVA6 this invalidation filter that will just invalidate sets of the L1 data cache. And consistency interface, we have this information about if the load and the stores are still pending or completed. Okay. So before starting the next one, I would say we have plenty of time. I would give you some time if you want to explore the exercises online, and then I would say we can have a 1 hour, 1 hour and a half for a break plus lunchtime, and we can restart at 1 p.m. So you have 25 minutes to play a bit with the code, to make me questions, and then from 12 I will be away. We can have some lunchtime, so I can also recover a bit and I can shut up a bit. So if you have any questions now, or otherwise you can play a bit around with the repo or have a break. I can also maybe also upload the slides.
Yes, I have a quick question.
Yeah.
I mean, I don't know if it is quick. Can you explain again a little bit the consistency problem? Because the coherence one for me is clear. The consistency one, if you can say just go on it again. Thank you.
Yeah. Problem is, if we have some store and some load that happens in CVA6 and ARA at the same time, we can have a problem because maybe CVA6 has a store, as a scalar store in the load store unit, right? While before we had ARA that is performing a vector store on a memory region. So you can suppose that we have a vector store followed by a scalar store, right? So ARA is writing here in memory, right? Then CVA6 receives a store, and just think about it. This store wants to take over the bus and write, for example, in one of these locations, right? So if it happens afterwards, we also need to respect this read after write hazard problem, right? So what we do is not to violate this instruction ordering, or you can think of the same with a load. If we want to load here and we have a read after write problem, we want first to store the whole vector in memory, because maybe CVA6 will need to fetch exactly from there. And this is a read after write, right? With the store and store, we had a write after write. We can have potentially a write after write in memory, right? So since these two are not synchronized, and since CVA6 is reading from the L1 data cache, we need to order these two scalar and vector operations to avoid these kinds of hazards, right? And to do so, we just force the ordering in program order, the ordering of the memory operations in program order. So if we have a vector store followed by a scalar load, for example, we make sure that this is completed so that we cannot incur in any read after write in memory, so that it has also somehow wiped out the respective sets of the cache, so that when we perform the load, if it's in the same set, we will also fetch again from L2 and then read again the updated value. I don't know if this clarified things a bit.
Yes, very clear. Thank you very much.
I was like, what's this noise? And it was my watch that I was pressing. So I can also ask you, do you prefer that we have still like 2 interfaces? Do you prefer that we finish the interfaces before lunch and we keep like the activities for after lunch? Or do you prefer to have 20 minutes now also to play around a bit?
I prefer doing after lunch personally.
So interfaces after lunch. Yeah, okay. Online? Who do you think?
I agree.
Just answering questions. So from where the store complete signals come from? So the store pending and store pending signals come both from CVA6 and from ARA, because CVA6 have some counters that count how many in-flight loads we have in ARA, how many in-flight stores we have in ARA. And like to speed up things, also we have this load complete and store complete. So store complete and load complete just bumped down the counters in CVA6, saying, hey, we had 3 in-flight load vector loads. Now we have one less, so that when CVA6 have 0 pending load, it can issue a scalar store, for example. And the store pending are just like these signals that say, hey, there is still a store pending on the other load store unit, so don't do anything, basically. Don't issue further vector load stores.
Yes, for sure.
Yeah, just some curiosity. If you then will work with ARA for performance and everything, you know, this coherence and consistency can also be disabled with this accelerator consistency enable thing. You can program it in software to disable these invalidations and this consistency and ordering interface, so that you can, if you are sure that you're not overlapping in memory between scalar and vector computation, you can just run super quick, but you need to be sure that this doesn't happen in software. So it's not a strictly legal way, RISC-V way of doing things. Yeah.
And let's say you want to enable this and then disable this. Do you have other way to do synchronization?
You can fence.
You have
You can software fence.
The software fence will wait that ARA is no more instruction in fact.
Yeah, it's waiting between it's waiting before issuing the next load or store, for example. So it will also wait before dispatching the store or load to ARA. So if you have a scalar operation, you fence, and then you have something else, nothing else memory related or accelerator related is given to ARA if this fence is not first satisfied. So if CVA6 does not get that last B from AXI, or everything else is completed in terms of load and committed.
So CVA6 during the partial decode knows at least if it's a lower.
Yeah. Yes.
Because anything.
Yes. Yeah.
Okay, and so the fence will work like you have all the RISC-V fence that, like if you do just a read fence, whatever, this is also implemented so that you only wait for the.
Okay, let me think. So it should work with read and write because it also knows if it's a read or a write. I think it should work even with release consistency, like meaning if you have atomic operations that also implicitly enforce a fence, meaning that it's like a release or acquire consistency. I think it should work. We never tried with atomic.
Okay.
Yeah. But I'm quite sure it should work. I never like tested this in particular. Yeah, we would need to test. Yeah, it should work. Like the hardware is there, but you are making me think that like usually also when we run it on Linux, we never tried some atomics that both are so accessing some critical sections both with R and CVA6. Yeah, we didn't try this thing yet. So it should be there. I would not bet all my money on that.
Okay.
That works, but it should work. Okay, if you don't have any other question from online, I can also start lunch now. You know, this is Switzerland. We need to have lunch before 12. Otherwise, we get kicked out from the country. Okay, so see you at 1, so that we can continue with RS interfaces. Bye, everyone. See you later.
Thank you. See you later.
Okay, we are here again. We will start in 2 minutes. Yeah, questions?
Yeah, I have a question. So let's say I have widening instructions, say from 32-bit to 64, and I have already the maximum L multiplier. How does it work? If I have already filled with 32-bit
You cannot do it, it's illegal. So if you have
okay.
already like called with 32 bits,
It says
the maximum, it's already detected at the coding time that the effective element width and then vector length of the would be like too high. Yeah.
And on the other hand, if I have, let's say, a partial or negative multiplier or like a fractional multiplier,
Yeah.
what happens to the rest of the vector register? Is it just not accessible or?
Yeah, in
Just
this case,
wasted
for the
space?
instruction, no, it's just there. So usually there is this undisturbed policy. If you're not working on the rest of the vector, you just leave it there. If yeah, it's agnostic, I think you can also write it at 1 and you, let's say, lose it. But yeah, usually the view of the vector register should be lower and the rest should not be touched if it's undisturbed policy.
Okay, but it's not like you're packing another vector there or whatever to use that space. Because
No, you cannot reuse that space.
Okay.
You cannot reuse the space. Yeah. I mean, in hardware you can do whatever you want,
yeah, but it's crazy.
but you need to simulate, like emulate a proper behavior, like respecting the byte layout. I will discuss also the byte layout. You need to kind of emulate the byte layout that is specified by RISC-V. So it's the same thing like if you go with register renaming, for example, and you have 90 physical registers, you can do whatever you want with your registers, but in the end, if you then store back to memory after a computation, after everything has happened between the load and the store, you should store exactly the same value as if you didn't do any tricks, basically.
Okay.
So it's up to you to emulate as you want. Also in ARA, we kind of emulate a different byte layout. You can optimize as much as you want. You can pack everything if you're not using the vectors, like the whole vector register space. Then it's up to you to keep consistency with the undisturbed policy so that you should have, in the end, 32 vector registers and the bytes that should figure in those vector registers, if you store them, are the ones as if you didn't have any tricks.
Okay.
Yeah.
Thanks.
Okay, we can go on. Is everything okay online?
Yes, we see a green screen.
Grande. Mitico. Mitico green screen. Okay. Okay, just a small summary. We are talking about interfaces. You know, we have talked about the instruction request response interface. So how CVA6 can issue instructions to ARA and how it can receive responses from ARA with a result or exception. Then we talked about the memory interface, AXI that goes directly to memory, and then coherence interface that is just used to invalidate sets of the L1 data cache of CVA6, and then an interface to keep memory ordering. So basically, consistency interface that is basically just say, hey, I have a store that is pending, I have pending load here, the load is finished, and so on. So now, question is, okay, everything up to this point is useful to run bare metal applications without any operating system. But what if we need to support memory translation from virtual to physical addresses? So we are in an environment with Linux, we have virtual memory, we have in ARA virtual addresses, and ARA has its own load store unit. How can we get away with it? So CVA6 already supports memory, supports virtual memory, virtual to physical address translation. This means that in CVA6's load store unit, we have a memory management unit that translates virtual addresses from the load store unit into physical ones that can be actually used with memory. And It also has a translation look-aside buffer, TLB, for France, which is just a small cache for the page table entries. So just a quick recap: when we need to translate a virtual to physical address, we have a structure that is managed by the operating system in memory that is called page table, that is just a lookup table that maps virtual addresses into physical ones. So these entries can be cached in this translation look-aside buffer. In CVA6, we just ask for a virtual address and we receive a physical address back. If the page table entry is not cached into the TLB, we will just have a page table walk. It is just a process of fetching and refilling the translation look-aside buffer with the correct page table entries. So this is CVA6. This is how CVA6 supports virtual memory in Linux, for example, and with operating systems. Question is, now we have ARA. ARA does not know anything of virtual and physical addresses. So we have extended the support for this virtual translation from CVA6 to ARA. So CVA6 with a CSR tells ARA if virtual memory is enabled or not. And if so, ARA will also reuse CVA6's MMU. So we add an MMU interface so that ARA's load store unit in the specific address generator will give the virtual address to the MMU of CVA6 and will get back the physical address and the exception if occurred. So this is basically a multiplexing of CVA6 MMU. So it cannot be used by both ARA and CVA6 at the same time. And ARA inside is a finite state machine that just asks for translation. And you know that we are using bursts, AXI bursts, for unit stride memory accesses with ARA. And this is cool because the AXI memory accesses by specification of AXI are already limited by the boundary of the 4 kilobyte pages. So we are basically asking for just one address translation per memory page burst. So there are not many address requests from ARA. While gather and scatter are worse, even worse, because they need one translation per address. So, you know, this involves also some exceptions handling, because if the MMU, if ARA is trying to store a read-only page, for example, and so the MMU receives a request for a translation of a store where the page is only read-only, we will have an exception. Or when we have a page fault, same thing, we have an exception. And ARA needs to handle this. If we are in the middle of a memory operation, that index will be saved in a specific CSR called vstart. So if we have processed the vector and we have loaded, this is the entire vector, and we have loaded up to this element I that causes the exception, then we will save I into vstart. Then we will answers back to CVA6 that we got an exception, so that CVA6 can commit, handle the exception by itself. And when we will have served this page fault, for example, the vector operation will start from vstart index. So vstart is basically saving the state of the index that caused the exception so that we can restart the execution from exactly that point. Okay. And then, yeah, then there is some handling of the exception also in ARA, because maybe we have fetched some operations already, so we need also to flush the microarchitectural state if we modified it with or after the faulty element. Okay. Nitty like detail, you can ask yourself how the previously described invalidation mechanism works with this, because you know, upon vector stores, we have said that we invalidate all the sets of CVA6 L1 data cache, right, through the snooping on the AW channel of AXI. The problem is that the cache of CVA6 is virtually indexed and physically tagged. So ARA here is working only with physical indices. And so how can we index the set if this is virtually indexed? So the trick is just that the cache is small enough so that the number of cache sets is actually lower than 4K. And if this is the case, the cache address index bits are just lower or equal than 12. And you know that the last 12 bits are always physical and never virtual. So the cache in the end is also physically indexed in practice. So with the physical address, we can use the physical information of the index and in the end invalidate the sets. But if this is not the case, so if you are increases the size of the cache, this is a problem. This can break down. So the number of the sets, not really the size of the cache, but the number of the sets should be lower or equal than 4K. Otherwise, we are not invalidating in the correct way anymore. Okay, so MMU interface that we have just described, ARA will ask for some, sorry, I got it wrong. ARA will ask for some virtual address translation. So it will issue a request with the virtual address saying if it's a store, because it's important for exception checking in the MMU. And then if virtual memory is enabled, this is just from the CSR of CV6, it will just answer with MMU valid answer, the physical address, and an exception if it occurred. Okay, so putting it all together, the interfaces between CVA6 memory and ARA are the AXI memory interfaces, both in CVA6 and ARA, the coherence interface between the invalidation filter and CVA6, taking the AW channel for ARA, so nothing new on ARA side. Then the main request and response, so this is just the instruction and result and exception, the MMU request interface to translate the addresses, and the consistency like, hey, pending store, pending load, store finish, and so on. These are all the interfaces that you can find in ARA CVA6 and L2. Just a super brief digression. You probably are familiar also with the X interface. Well, we also implemented it in a prototype of ARA, because the X interface is basically doing part of what this interface is also doing. So providing a way of giving instruction, getting exceptions back, giving the results, and so on. Problem is the X interface anyway does not specify anything in terms of memory, for example, and these interfaces would anyway remain custom. So all the interfaces to memory and all the interface for address translation, consistency, and coherence would remain custom. So if you think of implementing the X interface to get just a standard interface between the two guys, anyway, you will have some custom support. Truth to be told, also the specs of the X interfaces do not really 100% support this either, because right now the floating point, if I'm up to date, the floating point scalar register file and the integer scalar register file, so there is no way for the decoder and for the interface to understand if the accelerator needs a number from the scalar integer or from the scalar floating point register file. So anyway, since ARA also supports vector forwarding in floating point or scalar elements, this would prevent to use the vanilla X interface that you find in the specifications 1.0. Okay. Any questions on the interfaces? Also, let me check. I'm recording. Yes, I'm recording. Okay. So now let's have a quick look before the next hands-on experience on the byte layout of the vector register file in ARA and the byte layout prescribed by RISC-V specification, because this is a very important part of ARA. So ARA, let's take this example, ARA with 4 lanes, total size of the vector register file is 16 kibibyte, 4 kibibyte per lane, right? It is split among the lanes, and we have slices in every lane. So lane 0 will have this slice of the vector register file. So RISC-V byte layout, and this is also what Chris was asking before, the byte layout in the vector register file, going very easy on this, for normal vectors should be basically exactly what you find in memory. So a vector register file should just have in subsequent bytes the subsequent bytes that you also find in memory. So if this is V0 in the vector register file, you can expect exactly the same byte layout. No surprises. Problem is that this is not super friendly when you are implementing lanes. And this is why in ARA, we kind of emulate that particular layout, but the physical layout is a bit different. With ARA, to maximize parallelism and simplify mixed width operations, we store in the vector register file subsequent consecutive elements in consecutive lanes. So, for example, now we are loading a vector that has 16-bit elements. 16-bit elements. This is memory. This is V0 in the vector register file. And V0, you know that is split in different lanes, right? So this is the V0 chunk of lane 0, for example. This is the V0 chunk in lane 1. What the load unit does is like getting these guys over here and then assigning this to lane 0, this to lane 1, this to lane 2, and so on, so that we can write in parallel in the banks in the different lanes, right? So as you can see, this is not the byte, really the byte layout as prescribed by the specification, because we are fragmenting it into lanes, right? And this mapping depends on the element size. So, for example, the byte 1 in memory of so the upper byte of the first element. I don't find my cursor anymore. Yeah. Sorry. Okay. So we have the first element that is 2 bytes, 16-bit, right? And we have the second byte, the byte number 1 here, that is assigned to lane 0, because the whole element should be assigned to lane 0, right? But what if now we load elements by every element is just 1 byte? Every element will be assigned to a different lane, and this means that the same byte that we were seeing before will be assigned to lane 1. So before we had the same byte mapped in lane 0, now we have same byte in memory mapped to lane 1. So depending on the element width, the load unit should be able to shuffle the bytes and assigning them to different lanes to have a consecutive element in consecutive lanes. So the important message here is the same byte in memory can be mapped to different lanes depending on the element width. So this makes ARA, this forces ARA to reshuffle the byte layout of its vector registers in particular situations. For example, if since we have this tail element, this tail policy, as Chris was asking, we have this tail policy, we need to support also this tail policy that is undisturbed. Means that if we have a vector here and that in total can contain 32 elements, right? But now our tail of the strip mining loop is operating only on 17 elements, right? These elements shouldn't be touched. So we cannot really modify those elements. And since we are not overwriting the whole elements, and all these bytes are shuffled in the lanes, we cannot just overwrite these elements, for example, with a different byte layout, because otherwise we would remember that this register is stored with a different byte layout, different than the original one. So we are corrupting effectively these tail elements, because we have no way to reconstruct the original vector to store it back to memory. So before writing partially a vector, we need to reshuffle the vector. If this was encoded with element width 8, so like with this element, this byte encoding, we will, if we want to write it with EW16 partially, we need first to reshuffle this and change its byte layout to EW16, and then we can write it partially. So that we can also keep the information on the encoding. The encoding is unique, and we can reconstruct the vector when we store it back to memory. So this is also true when we have vector operations in lanes, right? Because lanes can only access the bytes that are present in a lane. So if we start reinterpreting a vector like with EW8, for example, then the lanes, for example, will need, lane 0 will need to access these elements as well, but these elements is not in lane 0. So we need to reshuffle the byte layout of the vector register V0 so that the correct bytes goes in the correct lanes. Same thing for loading and storing. Since we have a specific byte layout in the vector register file, and when we load or store, so when we store it to memory, for example, we need the natural byte layout that you would expect from a vector V, and this is just emulated in our vector register file. We need a reshuffling stage that reshuffles all the bytes and can order them properly, so that all the bytes are positioned in the correct way when we are storing it back. And this is done, only this last operation, since it's very important, and it always happens, is done on the fly directly by the load store unit. While all the other operations will be done by the slide unit. So when we need these byte layout changes, reshuffles, we will just inject through the ARA dispatcher. So in the decoding phase, we'll just dispatch some slide byte 0 with a source and a destination encoding that is different. So the slide unit will just reshuffle the elements, permutating the bytes, saving them back to the vector register so that they are ready to use. Okay, we can have a look, like a quick hands-on on this reshuffle thing to understand how the byte layout is handled in ARA. What we can do is trying to trigger a reshuffle in ARA. For example, initializing a vector just with 16 bits, right? But then loading one of them with an element width of 8, right? And then try to add them together. This is a situation in which we have two vectors. For example, the vector add will need to add V0 and V1 together, right? But V0, we have loaded it with element width 16-bit. V1, we have loaded it with element width 8, right? So the correct one single lane 0, for example, if we want to perform this in 16-bit, so with a standard element width in 16-bit, we'll already have the correct bit for V0, but the bytes of V1 will be shuffled, and part of the upper byte that will be needed for this operation is in another lane. So before the addition, a slide reshuffle will be injected into the slide unit to fix this byte layout first and get EW16, and then performing the addition. So we can try, you can also try, I will give you 5 minutes, then I will show the solution, we can go over it together. But the thing that you can try to do is try to VLE 8 in V0. then VLE 16 in V1, and then set with vset VLI the element width to 16, for example, and then VAdd between V0 and V1, right? This should be enough to trigger a reshuffle that we can see in like with the waveforms. Then the trick, so this is an operation that we add, right? And something we can try to understand if this impacts performance or not. Reshuffle here. So the idea here would be load bit 0, for example, with VLE 16. Sorry if it's like the other way around, I don't remember. V1 with VLE 8. So we are forcing here a element width of 8 for this operation, and we are forcing here an element width of 16 with this operation. If you want, you can also, to have things more clear, vset VLI forcing E16, forcing E8, even if it's not strictly necessary, and then E16, for example, and then we can VAdd. So here we can also load, like impose a let's say 2 times VL if this was VL, so that we can say, hey, we have, I don't know, 8 16-bit elements, and then we can fetch 16 bytes, so that we have the same number of bytes in both vector registers, right? Then we can operate again on AVL. Here we can just simplify this. And then we add V0 and V1. And this should be enough to trigger a reshuffle. So we can have a vector. Yeah, so these have so these are both 16 bytes and 16 bytes. We have this set I with 16 bits, for example. Here we will need set VLI 8 and 2n. So we are getting so we can start setting up a register with n 16-bit elements. So we load this, we load from A, and we are just fetching every element by element, this 16-bit vector. Then we can load 2 times n 8 from B. Then we can set up again n and 16 bits. So we have basically with this load 16 bytes in V0. In V1. So we're interpreting here the elements as 8-bit elements, and we are vector 16 8-bit elements, right? While here we are loading 16 bytes in bit 0, but we are interpreting it as 16-bit elements. So it's a vector of 8 16-bit elements, right? So we also expect the byte layout of V0 and V1 now to be different than before. Exactly. So this should trigger a reshuffle. The name now is reshuffle. The solution is exactly the same, I guess. Yeah, I was first loading 8, then 16, just like, and also storing them to memory, but the reshuffle is triggered at the BAT. So let's analyze the waves. So the important part is the reshuffle. We say that the reshuffle is triggered in the dispatcher. So let's start also to have a deeper look at these waveforms. So we have, RNCVSX. CVSX is our magical scalar core. We don't care about it for now because all the instructions are provided to ARA in the dispatcher through the accelerator request I. So we can check when we get valid vector instruction to the accelerator. Exactly, from here. So you see that here we are receiving instructions from the accelerator. This is a valid, ready valid interface. So here, valid and ready, request valid, request ready. So ARA is effectively getting the instruction and also answering back with the response interface. Oh. And we can see in ARA request what's the instruction that is decoded, right? For example, we have a load VLE, then we decode a VLE. Sorry, these were not valid instructions. Take the valid. So we get just one VLE here, one VLE here when it's valid, and then here it's again valid. We have the VAT, but first we have this slide down, right? This was not an instruction that was present in the program. You don't find this in the dump. So if I go in the dump and I have a reshuffle. So this is the disassembly of the program. You see that we have VLE8 here. We have VSET VLI. Who cares about this? We have VSET VLI, VLE, VSET VLI, VLE, VAD, VSE, right? So we don't have any slide here. But if you look at the waveforms, the dispatcher is giving to the sequencer load, V slide down, V add, and V store. So this is injected by the dispatcher. I can also show you when this happens. So in hardware source, a dispatcher. Okay, we have reshuffle stage. So we have some state for the dispatcher. Normal operation, we are just like decoding the operations. Waiting for idle, they're just like ancillary states, and then reshuffle. And in reshuffle, when we are reshuffling, we inject, here we inject this slide down operation. So this is just basically like an FSM that is injecting reshuffle operations until we have reshuffled the whole vector. And yes, so we build a reshuffle request if we see, for example, that we want to use a register, but the VSU, the element width does not match the element width of the vector registers, and we do it for the destination operand, for example, only if we are not overwriting the whole register, or we reshuffle the two source operands if this is an operation that happens in lane and we have a mismatch of the element width and the element width that was encoded in the instruction. So this operation is injected before the addition and will reshuffle a value that was being loaded, right? So right now we need to reshuffle the element that was loaded with the first load, right? So we expect also that when we load vector load unit, here we are loading the first register, and then with the slide unit, we also see that something is happening here. Red values because many of the values of the registers were not initialized. Anyway, this is sliding and reshuffling the whole vector register. That then is, the slide ends up here, and the addition starts already from here, right? Because it's training. So not the whole content of the vector register needs to be reshuffled to give valid elements to the ALU, because it can also the reshuffle can be trained. Okay, so to answer this, does the reshuffle impact performance? Yes, because anyway it's another operation on which you need to train, right? And the problem is that reshuffle, you have seen something that I didn't really stressed, is that this is training, like the add can train quite well with the slide, right? So the add starts here, the add starts here, even if the slide ends way later. But the slide started before. So you see that between the two yellow cursors that are the start of the reshuffle and the start of the addition is not that many cycles, right? Because we can chain. The problem is the load ends here, and we need to wait a lot before starting reshuffling. So we cannot really overlap the load and the reshuffle. This is a bit harder. So it impacts performance. The thing is that from a normal vector program, we don't expect the programmer to reinterpret the same vector registers with different element widths. So for example, if we have a mixed width operation and we want to pass from 8-bit and 8-bit to 16-bit, we always use V0 with 8-bit, always V1 to buffer 8-bit elements, and always V2 to buffer 16-bit elements. So it's not frequent in a good vector program that the same registers keeps on changing the element width with which is interpreted and encoded. So good programs should avoid changing element width in the same registers. Then, of course, what happens happens. If it happens, everything works out, but it's just slower. Okay. Any questions? Yeah.
Mathilde, may I ask related questions?
Yeah.
I know, like currently in the AI stuff, we have like some like gather operations to deal with the sparsity patterns in some kernels. And for the results coming from these gather operations, usually your vector length, for example, 50% sparsity, then your output vector will become only half of the length of the input vectors. In this case, you have a mismatch of the element width inside your vector operations. Do you have any like ideas how to like solve these problems?
So if you mean like you have a kernel, like if you're so when you are loading, when you're gathering operations, right? You will anyway set a vector length that depends on the length of the index vector, right? Because you first load the index vector, right? So you have
so the thing is like you can use a VR gather operation to do that if you have
VR gather. Sorry, yeah.
Yeah, so you load the entire vectors, and then like you use the index to select maybe 50% of from that like a vector to a smaller vectors. In this case, you have like you need to change the element width between these operations, and then yeah. So when you're loading it, it's like a twice of the length, and when you actually do the calculation, it's only half the length.
Yeah. So for sure, yeah. Like this is not really for reshuffling, right? Because we are keeping the same element width. It's just about changing VLAN.
Yes, yes, but we're just also like coming with extra overhead inside like a vector processor like Ara.
Like changing the vector length, if you're expecting like the element width, shouldn't hurt performance, provided that it will hurt performance because you are not running the full vector length, right? But that is intrinsic to your algorithm.
Okay, I see.
Right. So if you are taking full vectors, some of these are 0, right? And you say, okay, VR gather now, and we want to VR gather only these elements. I will just work on 2 elements. Anyway, you are working on 2 elements. So if you, okay, let's put it like this. There are of course some optimizations that you can do, right? Because you can also kind of continue assemble and compress also other indices in a vector to fill it completely, right? But this also changes a bit the algorithm, and I'm not fully sure that this will speed you up because you will need to compress a lot. The vector length of every vector will depend at runtime, right? So either you have a structured sparsity for which you know that for every chunk of your vector you will have, I don't know, 50% of zeros. So you also know the number of potentially non-zero elements, and maybe there you can play a bit more in compressing everything into a vector register. Otherwise, if you optimize, it can also come with other overhead. But there shouldn't be an intrinsic ARA-specific slowdown only because you are not writing the full vector. The slowdown comes from the fact that you are amortizing an instruction on a lower VL, right?
So but, like 8-bit, 16-bit multiplications, these kind of things, when you change the element width, there will be some problems. And so for the vector length, it's not, yeah.
Exactly. So changing the element width is not a problem per se. For example, if you have 3 different registers, okay, if you have just 2 registers like V0 and V1, right? And this is like 8 bits, and here you are converting to 16 bit with just a conversion, right? And yes. In your kernel, you are always using V0 to buffer 8-bit elements, and you're always using V1 to buffer 16-bit elements, you don't have any performance degradation. The performance degradation you have if, for example, you're doing double buffering, right?
Yeah.
And in your next iteration, you will use V0 to buffer 16-bit data, and then V1 to buffer 8-bit data. This is a terrible idea.
I see.
Because you are
I
changing
think
the element width of the same vector register.
probably like one relevant, like a more relevant cases would be like in the same use case when you do the sparsity like kernels, we usually like try to if it's a structured sparsity, we try to reduce the number of like the element width of the index that usually goes to below 8 bits even. So like 2 bits or 4 bits. Yes. And then like the tricks we play with is like we just when generate these indexes, we just encoding as like 8 bits. So we pack every 4 index together into a, like a 8 bits element. But because of like the accessing pattern of the ARA, this will cause some problems because the consecutive like 4 elements will be used by different vector lengths, right? So
if you're encoding it as 8-bit, so are you encoding it in software?
Yeah, in software.
So
like
if you're
when generates the data.
Okay, so if these are bytes, if every one of these are bytes, you're saying that you just encode your first index here, your second index here, and so on in software, right?
Yeah.
So the vector processor is anyway processing 8-bit data.
We just pack it like a more deeps, like so for example, for each index is only 2 bits, then we just like occupy only one 8-bit position, put pack 4 data into it.
Okay, so you are basically compressing this as much as you can.
Okay.
So yeah,
but this will cause problems in error, right? Yeah.
I'm just asking myself then when you do a vector load gather or whatever, how can you process sub bytes? So you have a special extension.
Yes, we need a hardware extension to deal with it.
So if you just have a hardware extension, you just say, okay, now ARA also supports EW4 instead of just EW8, 16, and whatever, right? And so if you implement another shuffling pattern so that the byte layout can also be encoded in EW4 sub byte, of course your interconnects will become more expensive because now they also need to go sub byte, right? But then everything should work out pretty well. So you are using, for example, EW4 in V0, right? When you VR gather taking this as VLX, I don't remember how it's written anyway, VLX4, right? Meaning that it will take, it will fetch indices
Index
from
4,
V0 in V4. Everything works out without performance penalty.
I see.
What you pay is the interconnect complexity.
Yeah, I see. Thank you.
Thank you for the questions. Okay, any other questions? Okay, so now I told you a lot of lies because the real byte layout mapping is even different than this. So what I told you is that the elements are saved in consecutive lanes, and this is true. The thing is that, for example, when you have 8 bits data elements, for example, your first element is saved in the first position of the element of lane 0, and second element, the first position of lane 1, and this is as I also told you. But then the second element is not put in the second position, is put in the middle. Okay, so we have another layer of reshuffling elements, meaning that the second element in a data packet will start, for example, always from the middle. In this case, B2, so that in mixed with operation, you see that the second element will always start from this byte, right? Also with 16-bit, we map in this way so that the byte of the second element is always going in the same byte of the word. So this is just an additional level of shuffling, and it was the shuffling proposed and suggested by the vector specification 0. I don't remember what, I think 0.7, I don't remember. Well, if it was 0.7, I think so, or it was 0.9, one of the two. Well, in one of these specifications, the specification of the byte layout became a bit more lane friendly and more similar to what we have in ARA. Then with 1.0, they returned to just saying the vector register file should exactly be what you have in memory. So now with ARA, we also need to emulate this. So they just for you, because the next hands-on will be a vector register file experience to understand the byte layout of ARA. And this is very important because if you want to debug anything in ARA, you need to know where to expect the bytes. So let's close this. Let's close. Okay, let's close this. So let's take the vector register file example. What we want to do now, I will show you. Okay, so we can try to load some data, perform some addition, and just observe in the waveforms the data layout, seeing if it's what we expect and if it matches this one that I've showed you. So we need to see if this byte layout is what we also find in ARA. So we can start performing operations on 8-bit elements and on 64 elements and see if they are mapped in that way, so that we can also check how they are mapped. Sorry. So since this is just with the waveform, if you want, you can also do it by yourself and experiment a bit, but I will start from my solution. Just to show you the waveforms, because I know that many of you don't have access to QuestaSim and waveforms. So what I'm doing here is getting some 16-bit elements, loading them. Sorry, I told you something wrong. So I first instantiate a vector of 32 bits, a vector of 16 bits, and then I just load 32 bits the first vector, 16 bits the second vector, and we can just have a look together how they are stored in the vector register file. Okay, so, we are loading now. Let's focus first on the first load. With this load, we are loading these 32-bit elements with ARA for lanes. You remember that ARA for lanes have a memory bandwidth of 32-bit times the number of lanes. So we have 128 bits per cycle on the data bus as memory bandwidth, right? So what we expect in cycle 0, we will load the first 4 elements, right? So we expect this from the bus, and then we expect 4, 5, 6, and 7 in the second cycle. Same thing, the bandwidth is, of course, exactly the same. We can just load many more elements if it's just 16-bit. So here we expect to load 0, 1, 2, 3, 4, 5, 6, 7. Actually, I'm using the same n number of elements. N is 8. So here we will fetch this 8 in just one cycle. Here we will take 2 cycles. So let's see if this is what happens. We go in the load unit. And in the load unit, you have the AXI R channel, the ones that we have checked also before. And we see this is the whole program. Here we are using the R channel of AXI, so probably something is happening here. So we have AXI bus R with 128 bits, right? And what we are loading in 2 cycles. You see it takes 2 cycles to... Here the clock period is exactly 1 nanosecond. So it takes 2 nanoseconds, 2 cycles for this to be loaded, right? And we see that the first of the 2 responses on the R channel is 0, 1, 2, and 3 on 32 bits, right? Exactly what we expected. And in the second cycle, we have 4, 5, 6, 7, right? Exactly what we expected. If we have a look at the second load instead, it just takes 1 cycle, right? And we have all the elements 16 bits. So 0, 1, 2, 3, 4, 5, 6, and 7. Exactly as expected, right? So now the question is, how are the 32-bit elements given to the lanes? So how is the byte layout when we give and we write back all these elements to the lanes? So the load unit is writing to 4 lanes, and every packet to every lane is 64-bit, as you see, right? So we see when the request is ready here, and this is the byte layout that we have in the 4 lanes. So we have lane 0, lane 1, lane 2, and lane 3, right? As we said, the first element, 32 bits, so half of this, is put in lane 0. This is the first element. Then the second element, 1, is put in the first element of lane 1. Then 2 is put as first element of lane 2. And 3 is put as first element of lane 3, right? And then 4 wraps up in lane 0, 5, 6, and 7, right? And this is somehow more or less how we would have expected it, right? But now let's look at how the 16 bits data are encoded in the lanes. So this is when the request to write back in the lanes happens. Result request from the load unit. And look at this. So we have 0, 1, 2, and 3. And then the next elements, so 4, is not in the first half of the vector register, right? It's exactly in the middle. So when we wrap up, the next element will go in the middle, 4, 5, 6, 7. And if we had 8 more data, we would continue like 8 would have been here in the middle, and then 8, 9, 10, 11, 12 in the middle, and so on, right? And this is exactly what we are seeing this. So with EW32, we have element 0, element 1. This is just with 2 lanes. 0, 1, then wraps up 2 and 3. With EW16 instead, EW16, we have element 0, element 1. Then we wraps up and we go at the middle of the vector, element 2 and element 3, right? So that you can see that if we only have 4 elements and we want to upsize them, it's very easy. Element 0 is always here, element 2 is always here, and same bytes belong to the same vector, even if mixed with operations. Do you have any questions on the real byte layout? Okay. So something we were also discussing before, as functional units are all SIMD-like, so they can compute in SIMD fashion. And this is quite handy since we support like multiple element widths. You know, the vector register file is working on 64-bit packets, so 64-bit data path. Of course, this is giving, for example, for an operation, 2 of this, guys, 64-bit. But we can compute, for example, 1 64-bit packet per cycle at a time. But if we are operating on smaller widths, narrower widths, sorry, for example, on 16 bits, well, this bus 64-bit becomes and can be read as 4 times 16 bits, right? And here, for sure, if we have 2 operands, we'll have another 4 times 16 entering the FPU and producing 4 times 16 per cycle, right? So this means that we can have 64 as a bit al cycle, regardless of the element width. So this can be, for example, one 64-bit element al cycle, or 4 16-bit elements al cycle, or 8 8-bit elements al cycle, okay, per cycle. So all RS unit can work in parallel like this, from the load unit to the store unit to the FPUs to the ALUs, slide unit, all the units are able to work in SIMD fashions. So let's also have a look at this, how it works in SIMD. Now I will give you 10 minutes so that you can try at least to write the program. This should be easy, meaning that there shouldn't be any new instructions at all. You can just try to, starting from, I don't know, VHEAD, only 8 elements. You start loading something in 64-bit. You set up everything in 64-bit. You can also avoid storing. And then you do the same. You can use different registers, but doing it on 8-bit elements, for example. So here you can use different registers if you want. Of course, this will be other, you can load this 8 with other vectors that you have initialized at 8-bit. So just try, then in 10 minutes, 8 minutes, we can have a look together at the waveforms. Okay, since I know that many of you do not have the waveforms, is it okay if we go on and I show with the waveforms what happens, or you still want some time? Okay, if you want some time, you can tell me or write it in the chat now. Okay, so we can just quickly show. Okay. Oh. Okay, so this exercise is just really some vector load in 8-bit and some vector addition in 8-bit, just to show same the capabilities, but this should be quite easy also to imagine. I think you more or less are all familiar with this SIMD units. Okay. So here we are loading the 8-bit elements, just to show you also the register file layout of this. So we are loading 8-bit elements v31 and v32. The first vector we expect it just to be from 0 to n. And you can see on the bus that this is the case. So on the load unit, our channel bus, we can see what's happening, what is being loaded, right? And yeah, so we can see that from here we start loading bytes 0, 1, 2, 3, 4, 5, 6, blah, 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 up to n, right? And same things, but like the other way around from n down to 1. So that the last element of the second vector is 1, the most significant element here is 1. So let's just see how this is saved and stored in the lanes. So load unit result request, when the load unit is writing into the lanes. You can see 0, 1, 2, 3, these are bytes, and then 4 in the middle, 5, 6, 7, and 8 in the middle of the middle, 9, A, B, C, D, E, F, and then we wrap up again, right? F, and then 1, 0, 1, 1, 1, 2, 1, 3, and then again 1, 4, 1, 15, 16, 17, and this is exactly as I showed you the byte layout mapping for the various elements, so, consecutive elements in consecutive lanes. So if we go in the lane, we can see that the ILU, SIMD ILU is called. When it has operand valid, you know, it's like 0, 1, 0, so 0, 4, 8, C. So all the elements shuffled, of course, element A and element B, and it's just like performing everything on these bytes, and in just one cycle, we have the result that is valid. So in the same cycle, we have this result that is already valid. Okay. So let's proceed. So this is just like to tell you how the dependencies are checked and kept in ARA. So every instruction passes through the dispatcher and then to the sequencer, right? And we said the main sequencer is the one keeping the scoreboard of ARA, and it's the one handling the dependencies, right? And the scoreboard is basically saying which instruction depends on which other instruction. So your scoreboard, you can really think of a structure that says we have instruction ID. We go from 0 to 7 instruction, because we can have 8 in-flight instructions, and just saying, hey, instruction number 3 depends on instruction number 4, for example. So we know in the scoreboard that there is a dependency between instruction 3 and instruction 4. So every instruction from the sequencer in which we have the scoreboard, so this is the sequencer. The instruction comes from the dispatcher and it's broadcasted to all the units of ARA. So to the lanes, to the vector load store unit, to the slide unit, and so on, right? Before it's broadcasted, we also attach to this instruction, we also attach some information. So this instruction will fetch some operands like VS1, VS2, and then VD, our destination vector register. Close to every register of this instruction here, we also attach, hey, there is a hazard on instruction ID 7, for example. So afterwards, when we go in the vector register file in the lane and we need to fetch operands, we know if one of the registers that we want to fetch have a hazard on which instruction, right? So I think that deserves a bit of attention is that all hazards to implement chaining, all hazards are enforced by a throttling of the source operand fetch of the dependent instruction. So this means, let me see, I don't remember if, yes, I have it afterwards. So we always control the source operand fetch. So if we have like a vload, for example, and vadd, right? And we are loading in v0, and this vadd is using v0 to do 2 times v0, for example, right? So here we have a read after write. So when we have vload that goes through the sequencer, and we update our read-write table and the scoreboard. Then when vadd is transiting into the sequencer, we attach here, if this was instruction 0, ID 0, we say, hey, this has a hazard on instruction 0. This has a hazard on instruction 0, right? So that this vadd will go into the lane asking for operands, knowing that these two v0 guys have a hazard, right? This means that when we ask for operands, we will fetch operands from v0 for the add only if the vload has written an element in the cycle before. Not only in the cycle before, it's a credit-based system, but when the vload writes an element, we say, hey, you have a credit to fetch one of these v0. When we fetch, we remove 1 credit. Then when vload writes another result in the vector register file, we have a credit more to let vadd fetch the next operand, removing the credit and so on. So this is a one-based credit system, and we always enforce it at the source. So even if we had a write after write or a write after read, we anyway enforce that the second instruction can or cannot fetch the source operands. Because if you think about it, if did I write it? I didn't write it. Yeah. Yeah, it's here. If source operands are not fetched, the results cannot be generated either, right? So if we control the operand fetch of the second operations, we are also implicitly controlling the write back of the destination register of the second operation, right? So also a write after write would be controlled, and also a write after read would be also controlled. So this is why if you open the sequencer, you can see that we always check, and we, in the lanes also, we always throttle only the operand source and never the destinations. Okay. Also something to note is that not all the operations can be trained. For example, vector slide operations cannot always be trained, right? Because if we have a vector slide that is basically slide down, so we take part of a vector and we slide it down into another vector register, right? What are we doing? We are fetching from index greater than 0, right, in the source operand. So if this is the source, we cannot really start fetching here if we have a read after write. So if the V slide down is sliding V0 in V1, and this V0 was written to by a VLoad, who knows, right? The VLoad is loading these elements starting from the beginning, right? But we cannot chain it, because otherwise when the load has written these elements, the slide down starts taking elements from half of the vector that was not already written to by the load, right? So these operations cannot really chain. I mean, you can optimize also the chain of this operation. It's just not straightforward because it depends on the slide amount. Okay, so this is how the operand source fetching is controlled. So if we have this V load and V add, right? In the lane, so this is a lane, and this is the load unit outside of the lane. You know, if the V load is not writing, the operand requester that will fetch V1 and V1 are also stalled. So this is a situation that can last forever if we have here a stall in the vector load unit, for example. V add does not start either, right? But as soon as the vector load unit writes in V1, right, we will have 1 credit for the operand requester. So every operand requester will have 1 credit if there is a hazard, and now there is, so that they can start fetching also 64-bit packet, right? To fetch again, they should wait until the load unit writes again. So if you look into the lane, we will have these operand requesters that will check if for example, we have a dependency on instruction ID 0, and on instruction ID 0, when the load unit writes, also forwards information about the ID that is writing. So when we match that we have the same hazard bit on the instruction that is writing, we bump 1 credit. And when there is a credit, we can also read in the next cycle. Okay, so brief introduction of vector reductions, how they are done in ARA. Vector reductions, you can think of, very easy. You have 2 vectors, you want to reduce them in just 1 scalar element. So, for example, V reduction sum, we want to add only the first element of VS2 to the sum of all the elements of VS1, so horizontal operations, to get just 1 scalar element. So, the consecutive elements are in consecutive lanes, right? So we cannot just reduce everything together. We need an intra-lane phase, so a phase of the reduction that is inside each lane, in which we reduce and get some partial accumulators, right? So in every lane, we will start reducing until every lane contains a partial accumulator, right? Then we will need an inter-lane phase in which we just logarithmically exchange data, the accumulators among the lanes, so that we can reduce finally. So we transfer the accumulators in the lanes logarithmically, we reduce, then we transfer, and then we have the very last the very last accumulator in just one lane. This is done through the slide unit. So we transfer the two temporary accumulators in the slide unit, and those are given to the lanes that already contained the accumulators. And this happens until we have everything in lane 0. You know, we have this accumulator, and if this is 64-bit, we can write it back immediately. But if this is like in this 64-bit, we have 4 16-bit elements, we still have a SIMD reduction phase in which we reduce all the SIMD values in just one 16-bit value scalar that we can write back. Floating point reductions are a bit worse, are a bit of a nightmare in terms of performance, because in a reduction, every element carries a dependency on the others because you need to reduce everything together, right? And floating point unit is pipelined. Depending on the element width, the pipeline of the floating point unit has a different number of stages. So we need to wait for sure R cycles before a new operations, not really, because we can start pushing everything into the FPU and start like using the pipeline registers as buffers. So we can just push everything inside. Yeah, we can just push everything inside, right? So we start operands 2, operand 3, and then when operand 0 and 1 are out, we can take them back and go on, right? We continue pushing things inside from one of the sides of the FPU operands, while in the other we just forward the result. So as you see, we are using the floating point pipeline register in the floating point unit as accumulators, so that in the end we will just have all the accumulators in the FPU, and then we will need yes to pay the latency of the floating point unit, because we will need to add 2 of the accumulators, then wait for the sum, and also add the final accumulator together. So in the end, we are paying way more than the number of elements divided by number of lanes, because we need also this for the intra-lane. So for what happens only in one lane, we also have this non-ideal term that depends on the number of pipeline stages. So in the end, it's like super linear with the number of stages if it's a power of 2. Okay, so now first serious hands-on. You know how to set up the vector length, you know how to VAD, you know, you will just need vmec instruction. You can find it in the ISA extension specifications. Try to write in Scratch. You have X Scratch, it's just something to have fun with, and you can compile it with Scratch. Try to build a vector product, vector.product. So you have 2 vectors, you multiply them together, and you get a scalar. Vector multiplications of 2 vectors, so you need to multiply them element-wise and then reduce. If you have questions, you can ask me. Otherwise, you have 15 minutes to try to do it. Remember that you can also use printf. Just 2 minutes and getting something to drink. So if you have questions, I will be back in 2 or 3 minutes. Okay, how is it going online? Everyone's dead. Let me know if I need to call the police. So, so something I wanted to show you is yeah, here we have a lot of applications already. It's very cool if you try also by yourself. I can started coding one of those, like the dot product. I can show you now how one of these applications is structured. So we just have a wrapper, right? And we can calculate, we can call different kernels, right? So we can call dot product on 64-bit, dot product on 32-bit, dot product on 16-bit, and whatever. And then you find all the kernels written in a separate folder, usually in kernel. And here you can see that are written either with intrinsics. So these are just C functions that you can also use to program a vector machine. Sorry, a vector machine. So we're using assembly for two reasons. For one main reason. Actually, you can see like the intrinsics are one-to-one with the assembly instruction, except for ASM volatile and these specifications of the variables, right? So you anyway need this one-to-one mapping, and with the if you compile with intrinsics, the compiler is anyway modifying a bit the order of the instruction. It can add something unexpected. So if you just want to see the effect of some instructions, you still need to go fully assembly, right? And if you start programming with these intrinsics, I personally don't think you are that way more productive, because in the end it's really a one-to-one. It's just a one-to-one mapping of the vector instructions. Anyway, also we studied a bit how is the performance of the intrinsics compared of just the and assembly optimized. So you can find both. And yeah, when you perform a dot product, you can do it in integer or in floating point, right? And between integer and floating point, you can really see the difference in performance of the reduction part, right? So the reduction part in the FPU will take its time, and then there will be when we have the reduced accumulators in every lane, there will also be the interlane phase. So we will also exchange data between the lanes. And then we will also have the SIMD reduction phase. I don't know if you tried already, but the code is just, you need to assemble everything into a scalar. So you can start cleaning up the accumulator, then loading the fragments of the vector, then multiply or directly multiply and accumulate if you can, and only at the very end, when you end up with one register only with your final vector, you can reduce. This I can show graphically. So instead of So you have two vectors, you need to multiply them, and you can do in many ways, right? You can start strip mining. So given that this vector is too long to be done in just one shot, you can strip mining in different iterations. For example, in iteration 0, you will process this chunk of the vector. You can start multiplying this. You will get another vector, and you can reduce it to a scalar. Then you can multiply the second chunk, reduce it to a scalar, and sum it to the previous accumulator, scalar accumulator. But this, you see, you are performing a lot of reductions, like at every cycle. Something you can do is exploit parallelism to instead multiply and accumulate the vectors. So if you have this strip mining loop, you first multiply on and create the first vector, but you don't reduce it to accumulator in an accumulator. In the second iteration, you can multiply and accumulate, so you get another vector accumulator. Same thing in the third round, and in the last round, you will end up with a single vector accumulator that then you can reduce, since the reduction is the least efficient operation. So let's just show how the vector dot product behaves. So you see, this is one of the typical R applications output. So in this case, there is also a check-in function. You shouldn't check with just your eyes. Everything is checked also by the tool. This is just a sanity check to see that we are not comparing none or trash that can become undetected. So you see, we have also vector runtime, scalar runtime. So something you can have a look at is the instruction that pass from the sequencer. So this is just also to show you how to interpret one of these applications. So this is one of the longest dot products that we have in the kernel. And this is just a kernel that is trying out a lot of different dot products. It's not measuring, we are not really measuring performance on this. We have like some benchmarks special that measure them one by one, because here we are also like reusing the same vector registers with different element width. And you can see that these incur a lot of slide down and reshuffles, right? Because we have LMAL equal to 8. So we have very big registers. We are reinterpreting them, and this implies that we need to slide down. And this is very bad for performance. Some of these guys get a vector runtime that is way higher than the scalar runtime, because all these operations shouldn't exist. So this means that the software is written in the wrong way. So let's just see how the reduction works. So we move, we clean up the accumulator, the scalar operator, we load and we load, and then we start multiplying. This is the move, and this is the reduction before the move. So the move is waiting for the reduction to be over, of course. So let's have a look at what happens in a lane. This is a floating point reduction. So we go in the FPU, so the module in the lane that contains the integer multiplier and the floating point unit, and also the integer divider, but who cares of the integer divider? Poor guy. So you can see that the floating point unit starts reducing. Wait a sec. Okay, so this is the state of the floating point unit. You see that no reduction, no reduction, no reduction when it's multiplying on multiplying and accumulating, and then it goes in 3 stages: intralane reduction. So in this first stage, the elements are reduced in accumulators in every lane, right? Then it goes in interlane reduction, transmission and receiving, because it's transmitting and then receiving some data to operate on them architecturally in a logarithmic fashion. Then after a while, interlane reduction is over, and we start with SIMD reduction. That is just if we are not operating on 64-bit, we also reduce the 64-bit packets on 32, 16, or 8-bit, depending. So you can see that in the first phase, this is like the, let's say, the most efficient phase, even if you can see that we are just computing with our FPNU. Invalid, invalid, result O, we should have a result valid, out valid O, and out ready I. You can see that in this phase here, we are processing 1 element per cycle. So you see, here we are just like getting operands into the FPU and just like pushing them inside, computing all the partial accumulators and keeping the partial accumulators inside the pipeline registers of the FPU. And then we will need, you know, from here on, we start the reduction of these accumulators into the lane, in the same lane. But since these accumulators are in the pipeline stages, we need to wait for them, the latency to go after the FPU, so to exit the FPU, then to push back again, wait for the latency, and at the very end, in the beginning, we can somehow amortize the latency because we have a lot of accumulators. So every cycle, we can push again inside the FPU new accumulators from the pipeline registers because the pipeline was full. But then we need to wait, let's say, half of the cycle again for the last 2 accumulators, and then the whole latency. Here you can see the whole latency of the pipeline registers, 5 nanoseconds, so 5 pipeline registers, like to completely go out again and be pushed in to get to the final result. And after, as soon as we have this result, we can start working on the interlane phase. So we can start getting this partial accumulator. We have 4 partial accumulator, 1 per lane, and we can reduce them and finally SIMD reduce directly in the last lane that we will write back in the vector register file. Okay. So now we can have a look at the repository structure. And then I thought I can quickly say what I thought to do now. Have a look at the repo structure, show you the flow on FPGA to implement everything on FPGA and to run kernels on Linux. I have some set up already, so we can cut some of the preparation there. And then we can have fun if you still have time. I think it will be in half an hour, so we will have 45 minutes. We can try to code new kernels. We can try to code something that is interesting to understand how vector programming work is understanding how to vectorize a matrix multiplication, or a stencil or a convolution, so we can do something like that together if you want. And then if you want, you can experiment single vector instructions that you like in the RISC-V tests, and you can also hunt for bugs in ARA. You will probably find some. So if you don't have any questions, we can start looking at the repository structure. So what we have used up to now in this hackathon was just part of the environment that I set up also for you. So as I was saying in the very beginning, maybe not all of you were already here. We have a pretty explicative README here. And following this, you should be able to install, configure, simulate, and everything. Thing is, installing the tools should be the hardest part. Then after it, everything should work out of the box. So README is just like getting started with some modules, getting the LLVM toolchain and the GCC toolchain installed, building Spike that is used to verify that the tests that we have written in software that automatically check some results are also correct when run on a golden simulator, because otherwise maybe we get something wrong, but the problem is the software. Then we have Verilator. We can verilate the ARA model. This is done also in the CI. So if you don't know, if you have doubts of whichever reason, you can also check the CI that is here in GitHub, workflows, CI. So the CI has a lot of stages. You can check the stage that you like the most. For example, verilate the processor. So you can, sorry, this one, two there. You can compile ARA, and here you're also verilating it. So this is how you would compile it with Verilator. If you have doubts, you can look at this. But then all the scripts should help you up to the verilation, spike simulation. So every kernel that we have can be run on ARA, just going into the apps directory and make bin and the name of the application. You can also do the same, but Spike run and then the name of the application, and this will be run on Spike instead of on ARA. If you can also make the tests, the RISC-V tests, and then run them on ARA using the same way that is described for the RTL simulations. So for RTL simulation, you just go in the hardware directory, you check out all the dependencies, you apply patches if you want to verilate, and then this is the line that you were also using during the hackathon. You just specify the name of the application that is found in the bin, apps bin folder, and you sim or simc, depending if you want to do waveforms in QuestaSim or not. Or if you want to use Verilator, you first need to verilate the model and then run simv instead of simc. Yes. So ideal dispatcher mode is just something that if you want to benchmark, if you're interested in experimenting a bit, this is basically replacing CVA6 with an ideal dispatcher, which is just a FIFO in which we first unroll the whole dynamic trace of the program. So it's basically an ideal module that is dispatching to ARA all the vector instructions with one instruction per cycle potentially. So it's basically a way to idealize the scalar core and see how much performance you can get with a better scalar core with one issue per cycle, or you can also expose the limitations in ARA, for example. If you want, you can also dump VCDs. You just need to compile the program with VCD dump equal to 1, and then simulate with VC dump equal to 1. I will now show you how this is done, because it's interesting if you want to do some some switching activity measurements for power simulations. And then, yeah, we also support some external benchmark suits. If you want, this is, for example, running a loop of every instruction in RISC-V in different configurations. Yeah, so this was the README. All the software that you can compile, because the flow is always compiling something and then running on the hardware or on Spike. All the applications are in the apps folder. You can find all the applications wrapped up in a main wrapper. They're just saying in loud voice, hey, this is a matmul. And then you always have the kernel this surrounded by some start timer and stop timer, which is basically reading the cycle time through the performance counters of CVA6. And then you run the kernel in between. So you can then get the timer value, and you can calculate some forms of performance ideality in the form of FPU utilization, for example. So the kernel of the floating point multiplication, for example, is in kernel. You can find different kernels depending on the size of the matrix, differently unrolled. It's very cool if this we can do it also at the very end, since matrix multiplication is a so famous problem. So apps, we have a lot of apps, and we can just compile them with make bin apps. Then we have the RISC-V tests. And here you can go and add your own tests for every instruction. So every instructions have some helping with some macros. We can play a bit with testing a single instruction. So once the load works and the store works, unit strided, all the others are also unlocked, kind of, and we can start testing, for example, addition, comparing it with a known pattern. This can also be generated by Python, by ChatGPT and Python. So you can also increase the number of test cases, finding some weird patterns, some weird instruction sequences. Here we are writing, we are testing with and without mask. So we are also loading some masks, and for every instruction of the vector specification, we run these tests. And the CI is always running these tests. Okay, so this for what concerns the apps folder. Then hardware folder, it should be quite self-explicative. The source code is in include and source, while the test bench is in TB. So test bench, we have just a wrapper that is, preloading the memory with the program, and then, instantiating the device under test. And it also has some facility to dump the VCD, so that if you dump with the VCD dump at 1, you can dump the VCD directly. Something that is very cool is that this is the parts that is automated in hardware, so the test bench helps you dumping the VCD. How you can control the dumpings? You can control it directly in software. So we have some facility also here. For example, Matmul has this facility. We can just say, you can just say, okay, if that VCD dump, which is exactly what you do when you compile with VCD dump Arathon, we have this memory mapped register at the SOC level. We just trigger it with +1 and -1. +1 when we want to start an event. In this case is the VCD dump. So when n, we are in the middle of the matrix multiplication kernel loop, so it will loop over n. For example, when n is equal to 8, we start dumping the VCD. When it's equal to 12, we can stop the VCD. This is just an example. You can also dump the VCD from start to end. It will just take forever because it's a post layout simulation usually. But the cool part is that with that trigger in software, you can basically say where you want to start the trigger, when you want to finish and stop the trigger, and the dump will be automatically dumped for you. Okay, source, everything we discussed now. So we have RSOC, that is the top level module. It's just like implementing the memory, the crossbar, some fake peripherals to be able to use printf, and then are instantiating the ARA system, which is CVA6 plus ARA. So the main part is ARA system plus SRAM plus crossbar plus some peripherals. Then ARA system is basically instantiating CVA6 and ARA. So you can see this CVA6. Then the W-width converter for the memory port of CVA6 that needs to be upsized. The invalidation filter that we discussed for memory coherence, and then ARA. And then final multiplexer to multiplex ARA and the CVA6 SAXI to the final crossbar in the SoC. And then you have ARA. So here you have the ARA module that is instantiating the dispatcher, the sequencer, the lanes, and all the modules in ARA. Okay, so last but not least, Cheshire. So here is the FPGA flow. There is something I can show you now. So how does this flow work? I can first draw it for you. So Cheshire is our SoC template that it's a synthesizable and also implementable SoC that works with a main core, CVA6. Okay, let's pretend that I have written CVA6 in this square. So CVA6, it has some L2 memory. CVA6 has its own L1. Also here we have a crossbar. And then a lot of peripherals. So this crossbar will have some conversions and will go in all the peripherals that you can think of, SPI, I2C for communication. Then you can also have your boot ROM to start like the computation and bootstrap the computation. So you can have a lot of peripherals here, and this can be also implemented on FPGA and also works with the peripherals on FPGA. So this is just a template. What we have done is integrating also a parameter to instantiate ARA in Cheshire, close to CVA6, so that Cheshire repo also instantiates ARA inside. So it has this submodule dependency ARA, right? And in ARA, we also have a target Cheshire to have the whole flow that reuses the files of Cheshire of the flow as much as possible, just modifying some configuration to make ARA work and compile also the Linux flow for ARA directly. So what I can demonstrate now to you, we can run in the README together first, and then I can demonstrate it. We can instantiate ARA in Cheshire, and then we can start compiling applications together with the compiler, the build root compiler for Linux. So we'll first get the build root compiler to compile Linux applications and the Linux itself. Then we will compile our applications with this compiler. We'll get to a Linux image with also our applications inside. We can also patch Cheshire to increase the size of the L2, for example, to host like larger programs for ARA. We can then build a bitstream for FPGA, Then we load this all this bitstream in an SD through SPI, and then we can run programs and start Linux on FPGA. And on FPGA will have this SoC, CVA6, and ARA. So I will show you. I'm sorry you cannot do it, but we don't have enough FPGAs. We have only 2 FPGAs, actually. Okay, no, it was okay. Okay. So here we're cloning Cheshire first. Can also remove this. We can remove this. And we can go and check, this is the ARA folder, Cheshire, where we have the README. Then here I have downloaded Cheshire. And for Cheshire, we will need to okay, everything is written here in an example flow. So I can just take the script that I can use since I'm internal here to the okay. So this is the script that you can also find online with just some information on our FPGAs. So what we need to do is to have our Cheshire, which we have, right? And with this Cheshire, we can export Cheshire root so that Cheshire root is exactly this checked out. Because it's not called like that. So this is Cheshire. Arathon V2. Okay. So now we are in Cheshire in the branch that supports ARA. What we can do is, of course, start making everything. So now I'm downloading all the dependencies for Cheshire, also downloading ARA, right? And what we will need to do is setting up ARA's root as well. This is just ancillary to our script. But what we need to do here is if we want to patch the hardware of Cheshire, for example, we do it to disable VGA that is interfering with some memory requests and upsizing Cheshire's memory a bit to go to 1 MB. Then we can start compiling the RBV RISC-V kernels that we want to play on Linux. So we can, I don't know, compile matrix multiplication, convolution, Jacobi for Linux. And this command will install the build root compiler and will compile those programs with the build root compiler. Then we can just issue this command, Linux image, and with this, the build root compiler will just make Linux together with the payload of our kernels, right? Then we can modify and cut the image of Linux to make it compatible with Cheshire, right? Then we just generate the bit stream. So we just synthesize everything for VCU 128. Then we flash the SD card with Linux through SPI, and then we just program the bit stream, and we are on it. We are already on FPGA with Linux. So now I cannot do this live because it takes too long, also compiling the Linux image and also compiling the bit stream. So I will just take one of the bit stream that we have already to show you how this works. Okay. So export tracer root here. root. Okay, so now we already have a Linux image that I prepared, and we can push on the FPGA. So what we can do is getting an FPGA. So we have this VCU04 that we can use. Okay, so we can start. Okay, here we are just pushing the Linux image that I've already compiled on the FPGA. This will take 10 minutes. So in these 10 minutes, we can go on. I can just explain to you what we can do in the next 40 minutes if you are still interested in this vectorization problem. So the first task can be, and this is really propedeutic and like useful to do to understand how vector computation works and how to exploit parallelism with vector applications. Try to vectorize matrix multiplication. So just perform a matrix multiplication between two n times n matrices. Or if you don't want to do it, you can also have a look at apps matmul, try to understand what's happening, which is not straightforward either if you are not used to it. And the other thing is like hunting bugs in RISC-V tests. Of course, you can also play with the other programs, but if you want, this is a bit more of let's choose an instruction that we like. Let's try to run it on ARA. If you have the waveforms, you can also check the waveforms and follow the instructions from CVA6 to ARA and to the lanes, follow the instruction flow, follow the data flow, and you can also add some new sequence of instructions and yeah, check out for bugs. Of course, if you have any other better idea, if you have questions, feel free to ask. Now I think we will need anyway other 5 minutes before demonstrating a program on FPGA. In the meantime, I can give you some insights for the matrix multiplication. I don't know how practical you are with matrix multiplication. I think you know what a matrix multiplication is, at least in theory. But the cool stuff is that there are like many algorithms to compute this. So what you want to do very easily with like the most straightforward inner product algorithm is just like multiplying these two columns and get this scalar element of the output matrix, right? So then you can start thinking of how to vectorize this. And yeah, you can load this with VLE, for example, and then load this with vload with stride, since we need to load a column, right? So this is not like the best performance you can have. And then reduce, right? So you just like multiply this together and you do a dot product basically. So in the end, you will have a reduction to get to one scalar element. And here you have a lot of intravector dependencies, right? The reduction is the example of this. So what you can also do is something different. Just imagine that the whole matrix fits your vector register file. Then you can start saying, okay, what is this vector? This vector is basically like this scalar elements multiplied times all these elements. Then and then this second element multiplied times these elements, and so on, right? All multiplied and accumulated together in a vector accumulator. So the idea is let's not go in a scalar accumulator. Let's keep the accumulator a vector, which is the same idea that we had before with the dot product, right? You can also always accumulate and reduce to a scalar, but if you keep it like a vector, you can minimize the number of dependencies that you are working on every time. So one possible approach is just to work on these vectors, and every vector is the multiplication of one of these vector here times scalar elements of the matrix A. There's just some intuition behind it, but you can think about it. So here it's still loading. Nice. So here I just opened the Word, UART. Just need to select the bit stream that I created yesterday. No. Here it's loading the bitstream. As soon as it's loaded, it's already programmed to boot from to know how to boot from SPI from the SD actually. Here Linux is booting. Will just take 2 or 3 minutes to boot. So in the meantime, what do you can also tell me also from online what you prefer to do if you want to do some kernels. We can do some kernels together. You can try with the matrix multiplication, or you can try to find some bugs. And I'm here for questions if there's something. Okay, Abemus Linux. So you can see that I started preloading some of the kernels here from Rivec. We have also some matrix multiplications and stuff. Just here to wanted to know that this is running on Linux. So they just XP on 256 elements. It's also automatically checking the results. I mean, it's not really entertaining, but it's just for you to know that this is fully running on ARA, and luckily the results is okay. So you can also put all the programs that you want on FPGA, and you can run them here. You can measure performance. Of course, there are interrupts here, so you need to know what you want to measure. If you want to measure performance without interrupts or with interrupts, anyway, you can use this platform to run vector programs. Okay.
Are we going to have these slides, what you are presenting?
Yeah, I will distribute the slides. So if you can provide me with your email, if you are interested, if you are not in Pulp Devil, internal mailing list, just give me your mail if you want also in the chat. I will now copy everything and distribute and give you a link of the slides.
Hello, Matteo. Hello.
Hey, Navaneeth. Navaneeth?
One question. Actually, so when you preload these programs, these are for a particular size or
Yeah, there is actually a limitation in Cheshire. I don't remember if it's 32 megabyte or what, but yeah, it can be changed. So I already tried, I already also uploaded something like 100 megabytes or something. So you're limited at a certain point from the size of your SD, but I managed to load way more. It needs some hacking if you want to load a very large data set, for example. But if you just stick with the normal programs that are creating numbers by themselves at runtime, you can load pretty much everything. It's just if you need these very big databases, maybe you need to hack a bit or open a pull request issue on Cheshire or work on the Cheshire limitation. It's not a real limitation, it's just a limitation of the flow.
okay.
Hi, Mato.
Hello.
Hi. I don't know if it's a good time now or not, but could you please explain a bit more the mask strategy you choose for the aura and the challenges you faces?
Yes. So let me see if I can open. Do you see the whiteboard?
Yes.
Nice. Okay, I don't promise you that my drawings will be good, but so oops, I didn't want to do this. Okay. So you know, okay, let's say these are our lanes, right? Then we have a specific unit called mask unit. Do you see my drawings?
Yes, yes.
Okay. I'm sorry for your eyes then. But okay, so these are our lanes, lane 0 to lane 3, for example. So the problem is the mask vectors are in the vector register file, right? And because of our layout, and this is just a choice and can be changed, because of our layout, the mask bits, so if this is a mask vector in memory, 1, 1, 0, for example. So this is like index 0, index 1, index 2, and so on, right? So in memory, all the mask vector is compressed together. So all the mask bits are on the least significant bits of the vector. Bye-bye, Lorenzo. Thank you. So all the mask bits are compressed together in the least significant positions of the vector in memory, right? Or this is anyway how you would expect from the specifications to find the vector mask bit. So because ARA have this shuffling of the byte 16 bits, 32 bit, and 64 bit, we take, for example, the mask vector from memory or when we create it, and we also save it with an encoding. For example, we save it with one encoding that can be EW8. This means that this packet of bits is treated as a single 8-bit element and is assigned to lane 0. Okay, because otherwise in the load store unit we would need the shuffling and shuffling stage that works at a bit granularity, and this would complicate the interconnect. So what we do is just packing bits, contiguous bits, in the vector register file of the lane. So this vector register file will contain the first 8 bits in this case, right? Then the second packet will be put in the second lane and so on, right? So since the very first bit should refer to index 0 of the vector, so of the bits of the elements that are in lane 0, and this should go in lane 1 by definition, but everything the packet is in lane 0, we need first to go in the mask unit. So we just take all this vector, this shuffled vector, we bring it to the mask unit, right? The mask unit is deshuffling at bit level at this point, because we are not on the memory interface, and the mask unit anyway needs to deshuffle and shuffle at bit level because it needs to support a lot of instructions that shuffle and reshuffle at bit level, but this is just in the mask unit. So we will reshuffle these guys here to get a deshuffled vector exactly as we would expect in memory, right? Then the mask unit takes these bits and says, oh, this is for lane 0. This is for lane 1, right? This is for lane 2, and so on, right? Thing is that the mask unit, what the mask unit is giving back to the lane are not just bits. They are byte strobes, right? Because if you remember, masking can be implemented in different ways. What we do in ARA is that, for example, we have an FPU in our lane. We have a result. We write in a result queue, and this result queue we write into the vector register file chunk of the lane, right? So this is a 64-bit bus. It means that it comes with a 8-bit byte strobe, right? So every byte of the data bus is controlled with a byte enable to write or not that byte in the vector register file. Why? Because we can also, this 64-bit packet can also contain 8 different 8-bit values. So here we need a byte strobe for every value. So what the mask is going to give to each lane is a byte strobe. So depending on the element width that we are operating on, it will take, for example, this is for lane 3, this is again for lane 0. So just imagine that you are working on 64-bit packets in the lane on 32-bit elements. So element 0 and element 1. We will need a byte strobe that is composed of 4 bits that will all be the same for one element and some bits that will be all the same for one element. If we want to write element 0, these byte strobes will be at 1, otherwise they will be at 0, right? So this is exactly what the mask unit is providing the lane. So the mask unit knows how many bits needs to take into consideration depending on the element width. It creates a byte strobe accordingly, and it forwards it to the lane so that this can be directly used to write or not write in the vector register file. So this is how masks are implemented in ARA. I think you're asking because you're interested in SPATs, right?
Yeah, exactly. And now it's clear.
Yeah. So in SPATs, I think it will work a bit differently because SPATs doesn't have this masking. So the bits in SPATs should be really like sequential, right? So depending on the vector byte layout, also this implementation changes a lot. I just make an example. So if we decided, and this is what we do in RXL, or if we decided to assign every bit to every lane, also contiguous bit to contiguous lanes, it means that we are also supporting EW1 encoding, right? So if we support EW1 encoding and the mask vector is also with EW1 encoding, every bit is already in the corresponding lane. So we will have, in this case, 1, 0, 1, 1 already. So the lane can also fetch locally its mask chunk, right? And do some and create its own byte strobe without passing through the mask unit. So the choice of the byte layout and the vector register file is crucial and will determine a lot of side effects.
Anyway, it's just
got it. Thank you so much.
No, thank you for the question. Okay, so let's look at the chat. I have two emails for now from Samuele and Lorenzo. Ciao, man.
Thanks a lot.
Thanks a lot.
I send you the email on your email.
Also in the chat if you want, or yeah, you can also send me an email. I'm listing them here. So right now I have Samuele and Lorenzo. Yes. Okay, guys, how are you online? Do you want to discuss anything else? Do you want to try something to get together? Otherwise, we could call it a day. Okay. So I guess we can also stop here if you don't have any questions. So I have 2 emails that ask me for the slides. So thanks a lot to everyone for participating. I hope you could learn something new or have a bit of fun. And see you next time.
Thank you very much.
Thank you very
Thank you,
much.
Mato.
Thank you very much. Thanks, Matteo.